What if I told you that over 90% of the universe remains an enigma, made up of forces so strange and elusive that they challenge the very essence of our understanding? Dark matter and dark energy, invisible and all-encompassing, are key players in the vast cosmic theater, yet we have barely scratched the surface in unraveling their secrets. As scientists continue to push the boundaries of our knowledge, new discoveries keep emerging, each more astonishing than the last. These celestial revelations not only redefine the nature of space itself, but also stir profound questions about the nature of existence, pushing us to reconsider everything we thought we knew. We find ourselves standing on the precipice of an awe-inspiring journey into the unknown, where the fundamental laws of physics are tested and where the unimaginable becomes possible. Consider the cosmic wonders that lie ahead of us, such as neutron stars, some of the most extraordinary remnants of stellar death. These dense, compact objects are the aftermath of massive stars that have exploded in a fiery supernova. But what makes them truly bizarre is their mind-boggling density. Imagine this. A neutron star contains the mass of about 1.5 suns, yet it is condensed into a sphere roughly 12 kilometers across. To put this into perspective, a single teaspoon of neutron star material would weigh as much as Mount Everest. The very fabric of matter itself seems to behave in unfamiliar ways here. In these stars, protons and electrons collapse under such extreme conditions, merging to form neutrons, which results in an incredibly dense, exotic state of matter that defies the laws of physics as we know them. Even more fascinating is the gravitational power of these neutron stars. Their gravitational fields are so intense that they warp the very fabric of space-time, a phenomenon that was first predicted by Albert Einstein in his groundbreaking theory of general relativity. This warping can be observed when light bends around these stars, creating an effect known as gravitational lensing. Furthermore, the immense gravitational pull of neutron stars can generate ripples in space-time itself, gravitational waves. These waves, caused by cataclysmic cosmic events, travel across the universe, carrying with them crucial information that could help scientists probe the nature of gravity and space itself. It's a cosmic dance of matter, gravity, and relativity, offering us a deeper understanding of the universe's most fundamental forces. Neutron stars don't stop there. They also possess magnetic fields that are billions of times stronger than Earth's. These magnetic forces channel charged particles into high-speed jets that shoot from their poles at nearly the speed of light. When these jets are aligned with our line of sight, they emit powerful beams of radiation, creating a phenomenon known as pulsars. Pulsars are remarkable in their consistency, often spinning several times per second and emitting regular bursts of energy like cosmic lighthouses. These rhythmic signals serve as natural cosmic clocks by allowing researchers to measure the passage of time with unprecedented precision. They provide us with an invaluable tool to explore parts of physics that remain beyond our grasp, offering clues into the nature of space-time, quantum mechanics, and the behavior of matter under extreme conditions. And yet there is another layer to the mystery. If a neutron star's mass exceeds a certain limit, it may collapse under its own gravity, eventually transforming into a black hole. This transition from neutron star to black hole is still one of the most profound puzzles in astrophysics. What happens in this critical moment when a star crosses the boundary into singularity? What lies beyond that event horizon, where the laws of physics break down? As scientists delve deeper into these questions, the boundaries of our knowledge continue to expand, revealing a cosmos far more mysterious than we ever imagined. The discovery of black holes has fundamentally altered our view of the universe. What was once a purely theoretical concept, born from the equations of Einstein's general relativity, is now a tangible reality. According to Einstein's theory, massive objects warp the space around them, creating a curvature that distorts the passage of time itself. When black holes were finally observed, they shattered our previous understanding of gravity, space, and time. These objects revealed that the universe is far more dynamic and unpredictable than we had thought. Far from being an empty expanse, space is an ever-shifting, intricate arena where time bends and warps under the influence of gravity. Within the depths of a black hole, the pull of gravity is so intense that nothing, not even light, can escape. This has profound implications for our understanding of reality, suggesting that space and time are far more malleable and interconnected than we ever realized. In these cosmic regions, the passage of time itself behaves differently. As objects approach the event horizon of a black hole, time seems to slow down. This effect, known as time dilation, means that the closer one gets to the black hole, the more time stretches, making the interaction between time and space far more intricate than we had imagined. In essence, black holes serve as a window into a realm where the fundamental principles of physics break down, providing us with a glimpse into the true nature of the universe. As we peer deeper into the cosmos, it becomes increasingly clear that our journey has only just begun. The universe is not a static, predictable place, but a dynamic, ever-changing expanse filled with strange and mysterious phenomena. From the extreme densities of neutron stars to the mind-bending distortions of black holes, these discoveries are just the beginning. Every breakthrough leads to new questions, new mysteries, and new wonders that challenge the limits of our understanding. The universe, in all its vastness, remains an untold story, one that we are only just beginning to explore. And as we continue to uncover its secrets, we are forced to confront a reality that is as awe-inspiring as it is humbling. The more we learn, the more we realize how much there is yet to discover. When we look up at the vastness of the cosmos, black holes emerge as one of the most profound and mysterious phenomena. These enigmatic regions of space, formed when massive stars collapse, offer us a glimpse into realms that stretch the boundaries of human understanding. Black holes are not just distant points in the universe. They are gateways to territories where our current scientific knowledge falters. When a star collapses into a black hole, it creates a singularity, an almost infinitely dense point where gravity is so strong that not even light can escape. This immense gravitational force bends space and time, leading to regions where the normal rules of physics seem to break down. One of the most intriguing aspects of black holes is the question of what happens to matter and energy when it crosses the event horizon, the boundary beyond which nothing can return. The possibility that information might be lost in these regions challenges foundational principles of physics, particularly the laws of causality and the conservation of information. These concepts are cornerstones of our understanding of the universe, and the mere idea that they might not hold in the presence of black holes has spurred intense debate among physicists. Researchers are now questioning whether our models of the universe need to be revised entirely, prompting a fundamental rethink of the laws that govern existence itself. As technology advances, we are gaining new tools to study these cosmic marvels. Instruments like gravitational wave detectors and cutting-edge telescopes are allowing us to observe the fringes of black holes in unprecedented detail. Each new discovery shifts our perspective, reminding us that black holes are not just theoretical curiosities. They are vital to unlocking the deepest secrets of the cosmos. These objects push the limits of what we know and challenge us to expand our minds. They hint at deeper truths about the nature of space, time, and reality, and in doing so, they invite us to reconsider our place in the universe. Similarly, the discovery of exoplanets, planets orbiting stars beyond our own solar system, has revolutionized our understanding of the diversity of planetary environments. Many of these exoplanets exist in conditions that are extreme by Earth standards. Some have temperatures so high that metals melt on their surfaces, while others experience crushing atmospheric pressures akin to those found deep beneath the ocean. These extreme conditions force scientists to rethink the processes of planetary formation and evolution, suggesting that the mechanisms shaping planets are far more complex than we previously imagined. One of the most fascinating aspects of exoplanets is the composition of their atmospheres. In some cases, these planets possess thick clouds made of exotic compounds like silicates and metal vapors, substances not found in the atmospheres of our own world. This discovery has profound implications for our understanding of how planetary atmospheres can form and survive under harsh conditions. By studying these alien atmospheres, scientists are gaining insights into the physical and chemical processes that occur on distant worlds, enriching our understanding of atmospheric dynamics across the universe. Moreover, these extreme exoplanets open up intriguing possibilities for life beyond Earth. At first glance, many of these planets might seem inhospitable, but research is revealing that life could potentially thrive in ways we never imagined. The presence of unusual elements and compounds in the atmospheres of some exoplanets suggests that life forms could evolve in radically different ways from anything we've encountered. This realization has profound implications for the search for extraterrestrial life, urging scientists to keep an open mind about the conditions under which life could exist. The study of these extreme environments also prompts us to rethink our place in the cosmos. As we discover exoplanets with conditions that stretch the limits of imagination, we are reminded of the vast, untapped possibilities that lie beyond our own world. Each new discovery pushes the boundaries of what we know, urging us to explore these distant worlds further and question our assumptions about life, chemistry, and the very nature of existence. In recent years, advances in observational technology have led to the identification of a wide range of celestial objects that challenge traditional categories in astronomy. One of the most striking examples is the discovery of rogue planets, planets that do not orbit a star, but instead drift freely through space. Scientists estimate that there may be billions of such planets scattered throughout our galaxy, raising important questions about the definition of a planet and its relationship to stellar systems. These rogue worlds do not fit neatly into the models we have used to understand planetary systems, suggesting that the universe is far more complex than our current classifications suggest. Adding to the intrigue is the mysterious object known as Oumuamua, which is believed to be the first interstellar visitor ever detected. Its elongated shape and rapid movement through space defy the characteristics typical of comets and asteroids. Even more puzzling was its unusual acceleration, which seemed to contradict the expectations based on gravitational forces alone. This object has sparked intense debates among scientists about the nature of celestial bodies and the very systems we use to categorize them. Oumuamua may very well represent a new class of objects in our universe, one that could rewrite the rules of astronomy. Another exciting discovery involves exoplanets found in unusual environments, particularly those orbiting binary star systems. These planets exhibit characteristics that challenge traditional models of planetary formation and climate. The existence of these worlds expands our understanding of how planets can form and survive in complex stellar systems, pushing the boundaries of what we know about the dynamics of planetary bodies. The rapid pace of discovery in the realm of black holes, exoplanets, and rogue celestial objects is transforming our understanding of the universe. Each new revelation reminds us that the cosmos is far more intricate and mysterious than we could have ever imagined. These findings invite us to reimagine the fundamental principles of physics, life, and existence itself, opening doors to new frontiers that will shape the future of scientific exploration for generations to come. The recent discovery of comets, often referred to as dusty snowballs with an unusual composition, particularly those rich in organic materials, has begun to reshape our understanding of the very building blocks of life in the universe. These celestial wanderers, once dismissed as mere ice and dust, have been found to contain complex organic compounds, which could offer crucial insights into the origins of life itself. The unexpected properties of these comets challenge long-held assumptions about where life-supporting elements might exist, suggesting that the conditions necessary for life could be far more widespread than previously imagined. As we continue to probe the depths of space, the knowledge we gather forces us to rethink our definitions and classifications of celestial objects. What we once considered fixed and rigid in our understanding of the cosmos is beginning to show signs of fluidity and complexity. These findings suggest that as our explorations progress, our interpretations of the universe must evolve to reflect the newfound intricacy and wonder that surrounds us. Similarly, the discovery of rogue planets, those mysterious solitary bodies that wander the galaxy without a parent star, has profoundly impacted the way scientists view planetary formation. For centuries, it was assumed that planets could only form in orbit around stars, but rogue planets challenge this notion, revealing a much more complex and dynamic process at play. These planets, which exist independently in the vast void of space, have been ejected from their original solar systems due to gravitational interactions. This unexpected revelation opens up new possibilities for how planets can form and thrive in a variety of environments, independent of a central star. The presence of rogue planets suggests that the process of planetary formation is far more intricate than once believed. Rather than being confined to the quiet and predictable orbits around stars, planets can be expelled into the dark expanses of space through chaotic events, such as close encounters with other massive celestial bodies. This discovery raises significant questions about the nature of these wandering planets. Could some of them harbor conditions suitable for life, despite their isolation from a central star? And how many more rogue planets might there be, lurking in the shadows of the galaxy, waiting to be discovered? The study of rogue planets also shines a light on the broader variety of planetary systems that could exist throughout the universe. The traditional model of planetary formation, one that assumes planets always form in the vicinity of stars, is now being questioned. Researchers are beginning to entertain the possibility that planets could form in a multitude of environments, some of which are vastly different from our own solar system. This expanded view of planetary formation forces us to broaden the scope of what we consider when studying the nature and diversity of planetary systems, prompting a complete rethinking of our place in the cosmos. Rogue planets, with their enigmatic and solitary existence, are challenging scientists to rethink everything we know about planetary formation. Every new discovery regarding these wandering worlds brings us one step closer to understanding the complex mechanisms that govern the evolution of planetary systems. As researchers continue to study the characteristics and distribution of rogue planets, we may uncover new pathways of planetary formation that were once thought to be beyond our reach. In this pursuit, each rogue planet offers a new clue, a new puzzle piece, in our ongoing effort to decode the mysteries of the universe. At the same time, the enigmatic phenomenon of fast radio bursts, FRBs, has captured the attention of scientists and astronomers alike. These incredibly brief yet extraordinarily powerful bursts of radio waves, originating from distant galaxies, last only milliseconds, but in that fleeting instant, they release as much energy as the sun might emit over the course of several years. The origins of these bursts remain shrouded in mystery, sparking intense curiosity and speculation about the fundamental nature of the universe. But the significance of FRBs goes beyond their sheer energy. These bursts act as cosmic beacons, providing an invaluable opportunity for researchers to study the interstellar medium, the matter that fills the space between stars and galaxies. As an FRB travels through this vast expanse, it interacts with the particles and magnetic fields that populate the interstellar void, leaving behind a unique signature. By analyzing this signature, scientists are able to gather important insights into the distribution, density, and evolution of matter across the universe. This allows them to probe the unseen aspects of the cosmos, furthering our understanding of the universe's composition and its long-term development. One of the most exciting aspects of FRBs is their potential connection to extreme astrophysical events. Some scientists propose that these bursts could be linked to neutron stars, particularly those that are rapidly spinning, or to exotic phenomena such as the collapse of massive stars. Each new discovery about the origin of FRBs forces us to reconsider our understanding of cosmic events and the mechanisms that drive them. With every new FRB detected, researchers are pushing the boundaries of what we know, uncovering new possibilities for the types of high-energy events that can generate such powerful emissions. These bursts, in their brief but intense flashes, offer a rare glimpse into the inner workings of the universe, prompting us to rethink what we know about its most enigmatic phenomena. In parallel, the quest to understand dark matter, one of the greatest mysteries in cosmology, continues to captivate the scientific community. Comprising roughly 27% of the universe, dark matter does not emit, absorb, or reflect light, rendering it invisible to traditional telescopes and measurements. Yet, its presence is indirectly detected through its gravitational effects on visible matter. Without the gravitational pull exerted by dark matter, galaxies would spin at such high speeds that they would disintegrate. This observation suggests that dark matter plays a crucial role in the formation and stability of galaxies, as well as the overall structure of the universe itself. Dark matter is also thought to be integral to the formation of galaxies in the early universe. Tiny fluctuations in the density of dark matter led to its clumping together, forming the scaffolding upon which galaxies and large-scale cosmic structures would eventually emerge. By studying the distribution and evolution of dark matter, scientists can gain critical insights into the history of the universe, from its earliest moments to its ongoing expansion. Understanding dark matter is essential for piecing together the broader cosmic puzzle, as it influences everything from galaxy formation to the large-scale structure of the universe. The ongoing study of these phenomena, the dusty snowball comets, rogue planets, fast radio bursts, and dark matter, represents a new frontier in our quest to understand the universe. With each discovery, we are forced to expand our understanding of the cosmos, challenging the old models and definitions that once guided our exploration. As we venture deeper into the unknown, we are reminded that the universe is far more complex and wondrous than we ever imagined. The more we learn, the more questions arise, and the more fascinating the universe becomes. The search for answers continues, and with every new revelation, the tapestry of the cosmos grows ever more intricate, leaving us in awe of the mysteries that lie just beyond our reach. Dark matter plays a pivotal role in shaping our understanding of the universe and its evolution. This mysterious substance, which cannot be directly observed, exerts a gravitational influence on visible matter, affecting the behavior of galaxies and the cosmic structures they form. One of the most significant contributions of dark matter to our comprehension of the cosmos is its impact on the cosmic web, a vast, interconnected network of galaxies linked by filaments made predominantly of dark matter. This intricate structure serves as the backbone of the universe, influencing how galaxies are distributed and how they interact over cosmic time. The behavior of galaxies within the cosmic web, including their collisions and mergers, offers essential insights into the dynamic processes that govern the universe's evolution. These interactions, driven by both the visible matter of stars and the invisible influence of dark matter, are key to understanding the formation and growth of galaxy clusters, some of the largest and most massive structures in the universe. The relationship between dark matter and visible matter is central to unraveling the mysteries of these colossal structures and their role in cosmic evolution. As scientists continue to probe the nature of dark matter, they push the boundaries of astrophysics, refining their models and testing new hypotheses through both theoretical work and experimental observations. These efforts are critical not only for advancing our knowledge of the cosmos, but also for unlocking the secrets of one of the most elusive substances in nature. Dark matter's enigmatic influence raises profound questions about the fundamental nature of reality itself, propelling humanity's quest for knowledge into deeper realms of the universe. Each discovery brings us closer to understanding the cosmic forces at play, offering glimpses into the very fabric of existence. Parallel to the search for dark matter is the ongoing exploration of dark energy, a force that has become one of the most perplexing mysteries of modern cosmology. In the late 1990s, astronomers made a groundbreaking discovery. Galaxies were not merely drifting apart, as had been expected from the effects of the Big Bang. Instead, they were accelerating away from each other at an ever-increasing rate. This revelation suggested the presence of an unknown force, one that counteracts the attractive pull of gravity. This mysterious force came to be known as dark energy, and it is now believed to account for approximately 70% of the total energy content of the universe. Several theoretical models have been proposed to explain the nature of dark energy. One of the most intriguing is the cosmological constant, a concept introduced by Albert Einstein over a century ago. The cosmological constant posits that dark energy is a fixed energy density that permeates all of space, remaining constant even as the universe continues to expand. This model aligns with current observational data, but questions remain about whether dark energy is truly constant or whether it changes over time. A competing theory, known as quintessence, suggests that dark energy might evolve, with its strength fluctuating over cosmic epochs. If this theory is correct, dark energy could have a profound impact on the universe's fate, potentially influencing the future expansion or contraction of the cosmos. Another line of inquiry challenges the very foundations of our understanding of gravity. Some scientists propose that the laws of gravity may not be universal and may behave differently on large cosmic scales compared to smaller galactic ones. This theory, known as modified gravity, suggests that the acceleration of the universe's expansion could be explained by adjustments to the laws of gravity, rather than by the presence of dark energy. Such a radical shift in our understanding of gravity would require a fundamental reevaluation of general relativity, the framework that has long guided our understanding of the universe's large-scale structure. As research into dark energy continues to advance, it remains at the forefront of cosmological studies. Astrophysicists and astronomers are developing increasingly sophisticated telescope and experimental methods to gather more precise data. These tools will allow scientists to test competing theories and refine their models, bringing us closer to unraveling the true nature of dark energy. Whether dark energy is a constant property of space, a dynamic force, or an indication that our grasp of gravity is incomplete, its discovery could have profound implications for our understanding of the universe's past, present, and future. Ultimately, unlocking the mysteries of dark energy may hold the key not only to the fate of the cosmos, but to deeper insights into the very nature of reality itself. In parallel, cosmic rays, high-energy particles that travel through space at nearly the speed of light, offer another window into the extremes of the universe. These particles originate from a variety of sources, including supernovae, black holes, and even distant galaxies. When cosmic rays interact with the Earth's atmosphere, they generate secondary particles that can be detected by instruments on the ground. By studying these high-energy particles, scientists gain valuable information about the most violent and energetic processes in the universe. However, the importance of cosmic rays extends beyond their role in understanding extreme cosmic phenomena. These particles may hold clues about the existence of extraterrestrial life and provide insight into the conditions found on distant planets and moons. When cosmic rays collide with surfaces in space, they can trigger chemical reactions and produce distinct radiation patterns. By analyzing these interactions, scientists can infer the composition of distant worlds, including those within our solar system and in far-flung star systems. Patterns of emissions or chemical signatures found in these cosmic ray interactions may reveal environments that could support life or harbor the building blocks of organic molecules. This makes cosmic rays not just a tool for understanding the violent forces at work in the universe, but also a potential key to unlocking the mysteries of life beyond Earth. Through the study of cosmic rays, scientists continue to search for evidence of life elsewhere in the cosmos, expanding our understanding of what it means to live in a universe that is perhaps more inhabited than we ever imagined. As our knowledge of dark matter, dark energy, and cosmic rays continues to grow, so too does our understanding of the cosmos. The ongoing quest to unravel the mysteries of the universe drives the development of new technologies, new theories, and new ways of thinking about the very fabric of reality. With each new discovery, we move a step closer to comprehending the universe's most profound secrets, secrets that have the power to transform our understanding of the cosmos and our place within it. Cosmic rays, some of the most energetic particles in the universe, are not only captivating in their own right, but also serve as a potential window into a much deeper mystery. These high-energy particles might hold more than just clues about our universe. They could also give us insight into the possibility of life beyond Earth. Recent studies suggest that some cosmic rays could be produced or influenced by phenomena that point to biological activity, or at the very least, provide hints about the conditions that might exist on alien worlds. One intriguing possibility is that certain cosmic rays could generate radiation signatures detectable in regions where microbial life might exist. For instance, if we were to discover significant quantities of specific isotopes known to be linked with biological processes, it could offer a tantalizing indication that life exists or has existed in distant corners of the cosmos. Cosmic rays, in this light, aren't merely about understanding the phenomena themselves, but could play a crucial role in answering one of humanity's most profound questions. Are we alone in the universe? With every new discovery related to cosmic rays, we edge closer to expanding our knowledge of life beyond Earth. These cosmic phenomena could become stepping stones in our search for extraterrestrial existence. As researchers continue to delve into the mysteries of cosmic rays, their findings not only fuel scientific inquiry, but also ignite our imagination, inspiring us to dream of life among the stars. This pursuit, in essence, transforms the very enigma of the cosmos into something more, a potential roadmap leading us closer to answers we've long wondered about. Parallel to these advancements, an even more mind-boggling revelation has emerged: the discovery of phantom galaxies. These enigmatic galaxies appear to exist without the dark matter typically thought to be essential for galaxy formation. Their existence challenges our long-standing beliefs and the very laws of gravity as we understand them. In a cosmos where dark matter is seen as the scaffolding that holds galaxies together, phantom galaxies defy these assumptions, suggesting that some galaxies might form under entirely different conditions or frameworks. This unexpected discovery is reshaping the way astronomers think about the universe and pushing them to reconsider existing models of galaxy formation. The implications of phantom galaxies extend far beyond the realm of theoretical physics. If such galaxies can exist without dark matter, it raises important questions about the nature of our cosmic neighborhood. How could galaxies function without the influence of dark matter? This realization opens up the possibility that the universe's structure may be far more complex than we ever imagined, with pathways for galaxy formation that differ from the norms. This shift could eventually lead to groundbreaking new discoveries, reshaping our understanding of the forces that govern the cosmos. This new paradigm encourages a deeper exploration of the unknown, prompting scientists to rethink not just the formation of galaxies, but the very fabric of the universe itself. The discovery of phantom galaxies is an invitation to broaden our horizons, revealing that the universe may be far richer and more mysterious than we had ever envisioned. Every new question raised by these findings serves as a reminder that the cosmos holds secrets yet to be uncovered, pushing us ever further into the vast expanse of space. In the history of astronomical discovery, few events have been as transformative as the discovery of the Galilean moons in 1610. These 4 moons of Jupiter, Io, Europa, Ganymede, and Callisto, changed the course of science forever. Their discovery not only provided the first direct evidence of celestial bodies orbiting a planet other than Earth, but it also marked the downfall of the geocentric model of the universe, which posited that everything revolved around Earth. This discovery paved the way for the acceptance of the heliocentric model, which placed the Sun at the center of our solar system. Each of the Galilean moons has its own distinct and fascinating characteristics. Io, the most volcanically active body in the solar system, is home to hundreds of volcanoes, some of which expel fountains of lava that can reach staggering heights. Europa, with its thick icy shell, is believed to harbor a vast hidden ocean beneath, making it one of the prime candidates in the search for extraterrestrial life. Ganymede, the largest moon in the solar system, possesses its own magnetic field and shows signs of geological activity, further deepening the mystery of its formation and evolution. Callisto, heavily cratered and ancient, tells a story of a tumultuous history, having endured numerous impacts over billions of years. The Galilean moons not only reshaped our understanding of the solar system, but also led to a fundamental shift in how we view moons in general. No longer merely seen as secondary objects, moons were recognized for their complexity and diversity, offering key insights into the dynamics of planetary systems. This discovery pushed astronomers to search for similar multi-moon systems around other planets, expanding the scope of our exploration beyond just our own solar system. As we continue to discover new exoplanets and their moons, the lessons learned from the Galilean moons serve as a cornerstone, guiding our exploration of distant worlds. These moons remind us that the universe is full of wonders, and by studying our own celestial neighbors, we can gain valuable insights into the possibilities of life and the mechanics of other star systems. Moreover, the discovery of gravitational waves has fundamentally altered our understanding of the universe. These ripples in the fabric of space-time were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, and they are generated by some of the most violent and energetic events in the cosmos, such as the collision of black holes or neutron stars. Before the detection of gravitational waves, our knowledge of the universe was primarily based on electromagnetic waves, light, radio waves, and other forms of radiation that we could observe using telescopes. Gravitational waves, however, offer an entirely new method of observation, providing a fresh way of looking at the cosmos. What makes gravitational waves so remarkable is their ability to travel through matter unimpeded, unlike light, which can be blocked or absorbed by dust and gas. When gravitational waves are detected, they carry with them crucial information about their origins. For example, while light from a merging black hole might be too faint to detect, the gravitational waves from such an event can reveal important details about the masses and behaviors of these objects. This discovery has effectively expanded the toolkit available to astronomers and physicists, enabling them to observe and understand phenomena that were previously invisible to us. In essence, gravitational waves have opened up an entirely new chapter in the study of astrophysics, offering a deeper understanding of the most extreme events in the universe. This discovery marks a pivotal moment in our quest to unravel the mysteries of space-time and the fundamental forces that govern the cosmos, pushing us ever closer to understanding the nature of the universe in ways we had never before imagined. The breakthrough in our understanding of the universe has been nothing short of revolutionary, as recent discoveries have opened up entirely new avenues of exploration. One of the most striking developments in modern astronomy is the advent of multi-messenger astronomy, a transformative approach that allows scientists to observe the cosmos in ways never before imagined. By combining data from gravitational waves, light, and other cosmic signals, astronomers can now create a far more comprehensive picture of cataclysmic events. In essence, this approach provides a more holistic understanding of the universe, unveiling previously hidden phenomena. For instance, the detection of gravitational waves emanating from a neutron star merger marked a pivotal moment in this new era. This event was not only captured through the ripples in space-time, but was also simultaneously observed across the electromagnetic spectrum. From the high-energy gamma rays to the optical light visible to the human eye, astronomers were able to capture this cosmic collision in unprecedented detail. This convergence of different types of data allows scientists to piece together a far richer narrative of what occurred during such events. It highlights the remarkable interconnectedness of the universe, where different phenomena, often perceived as separate, are deeply intertwined. Gravitational waves themselves have revolutionized how we observe the cosmos. They offer us an entirely new window into the universe, providing insights into processes that were once hidden from our reach. By studying these waves, we are uncovering cosmic events and mechanisms that have eluded traditional observation methods. This, in turn, enables collaborations between researchers who specialize in various forms of cosmic data, bringing together a wide range of tools and techniques to better understand the universe. As we continue to refine detection technologies and improve the sensitivity of our instruments, the possibilities seem endless. Who knows what other astonishing discoveries lie in the depths of space-time waiting to be uncovered? One of the most thrilling new chapters in our understanding of the cosmos revolves around the collision of galaxies. While these encounters may seem chaotic at first glance, they are far more than just destructive events. They represent a cosmic dance that plays a key role in shaping the future of galaxies. When two galaxies collide, it can trigger explosive bursts of star formation, a phenomenon known as starbursts. As the immense gravitational forces between the galaxies compress gas and dust, they create the perfect environment for the rapid formation of thousands of new stars, completely reshaping the galactic structure. This process also offers a rare and invaluable opportunity to study the role of dark matter in galaxy formation. Dark matter, which makes up a substantial portion of the universe's mass, is invisible to traditional observation techniques, yet its presence can be inferred by its gravitational effects. During a galactic collision, the dark matter halos surrounding each galaxy interact with each other in ways that can be detected indirectly. By observing these interactions, scientists can map the distribution of dark matter and gain critical insights into its role in the formation, stability, and evolution of galaxies. Moreover, the morphology of the merged galaxies often reveals important clues about their past. As galaxies collide, they can form distinctive features such as tidal tails or loops, the result of intense gravitational interactions. These structures not only offer insight into the mechanics of the collision itself, but also provide a glimpse into the galaxy's evolutionary histories. By studying these features, astronomers can begin to piece together the long and complex timeline of how galaxies evolve over billions of years. Each collision becomes a chapter in the broader story of the cosmos, shedding light on the ongoing transformation of the universe. The aftermath of these galactic mergers raises profound questions about the fate of galaxies. When galaxies collide, the end result may be the formation of a larger galaxy with a more intricate and diverse structure. This highlights an important truth about the universe. It is not static, but rather, it is a dynamic, ever-evolving entity. Galaxies are constantly shaped and reshaped by their interactions, and these interactions are key to understanding how the universe has come to be what it is today. The discoveries surrounding galactic mergers remind us that every star, every galaxy, is a living testament to the cosmos' ongoing transformation, carrying the history of its past encounters and the potential for future evolution. Another key revelation in the study of the universe comes from the cosmic microwave background, CMB radiation, a remnant of the Big Bang. The CMB has long been considered a treasure trove for researchers trying to decode the early universe. One of the most fascinating aspects of the CMB is its remarkable uniformity across vast stretches of space. The temperature fluctuations are incredibly slight, suggesting that the universe in its infancy was smooth and homogeneous. This smoothness would eventually lead to the formation of the cosmic structures we observe today: galaxies, stars, and clusters. Yet, within this apparent uniformity, scientists have also discovered intriguing anomalies, the most famous being the cold spot. This region of the CMB appears cooler than expected and has led to various theories regarding its origin. Some researchers speculate that this anomaly could be the result of large-scale cosmic structures, such as a massive void or a superstructure that might stretch across billions of light years. Others have even suggested that it could be a sign of a multiverse, where our universe interacts with others in ways that affect the CMB. The cold spot, along with other such anomalies, raises fascinating questions about the very nature of the early universe and whether current models of cosmic evolution can fully account for such strange findings. These discoveries challenge our understanding of the universe and push the boundaries of what we know about its origins and evolution. The cold and hot patches found in the CMB force scientists to reconsider their theories about the initial conditions of the universe and whether these conditions align with our current models. What does it mean for the universe to have such anomalies? Are these simply random fluctuations, or are they indicative of something far more profound? The journey of discovery is far from over, and as new data emerges, our understanding of the cosmos will continue to evolve, revealing deeper mysteries and wonders. The universe, with all its vastness, complexity, and interconnectedness, has only begun to reveal its secrets. Each discovery builds upon the last, gradually expanding our comprehension of the forces at play, from the smallest particles to the largest cosmic structures. With each new finding, we are not only uncovering the past of the universe, but also peering into its future, gaining insights that could change our understanding of existence itself. The story of the universe is one that is still being written, and we are fortunate to be living in a time when we can be a part of it. Advanced studies of polarization within the cosmic microwave background, CMB, have opened an extraordinary window into the universe's earliest moments, revealing hidden clues about some of the most powerful and enigmatic phenomena in cosmic history. Among these phenomena are gravitational waves, ripples in the fabric of spacetime believed to have been produced during the universe's inflationary phase. These waves are the echoes of intense events that occurred mere moments after the Big Bang, And by detecting subtle polarization patterns in the CMB, scientists are able to trace these ripples back to their origin. This ability to peer into the violence of the early universe allows researchers to enhance our understanding of the cosmos during its infancy. Each new discovery, as researchers sift through mountains of data, adds depth to our knowledge, uncovering layers of complexity that we had not anticipated. The cosmic microwave background, long regarded as a mere relic of the past, has proven to be much more than that. It is, in fact, a crucial relic that acts as a time capsule, holding vital clues about the formation and evolution of the universe. With each new finding, we do not only answer questions that have lingered for centuries, but we are also presented with new mysteries that invite us to explore even deeper. The CMB acts as a map to the very beginnings of our universe, offering insight into how it was formed, structured, and possibly even into what its ultimate fate may be. In parallel to these cosmic discoveries, recent surveys of ultra-diffuse galaxies have significantly altered our understanding of galaxy formation, throwing conventional models into question. Unlike the more typical, densely packed galaxies, ultra-diffuse galaxies are unique in that they contain an expansive spread of stars, but very little visible matter. This characteristic defies expectations, as such galaxies appear to flourish without the substantial amounts of dark matter or gas that are typically thought necessary for galaxy formation. Traditional theories of galaxy formation suggest that galaxies emerge as mass accumulates over time through gravitational attraction and interactions with neighboring galaxies. However, the existence of ultra-diffuse galaxies challenges this notion. It suggests that the process of galaxy formation may not be as straightforward as previously believed. Some of these galaxies are found within clusters of galaxies, leading scientists to propose that interactions within these environments may play a significant role in shaping the galaxies. These interactions may strip away essential gas and dark matter, leaving behind galaxies that are vast and star-rich, but strikingly diffuse. Moreover, the discovery of ultra-diffuse galaxies opens up the possibility of alternative formation scenarios. Some researchers speculate that these galaxies might have formed through processes such as direct collapse or other mechanisms that do not neatly fit within the traditional models of galaxy evolution. The question now arises, are these galaxies simply an outlier in the grand picture of galaxy evolution, or do they represent a distinct path of development altogether? As researchers continue to investigate, early observations suggest a variety of factors at play, including environmental influences and variations in chemical composition. The existence of these galaxies challenges long-held beliefs and urges astronomers to reconsider the fundamental processes that drive galaxy formation. These puzzling structures invite new lines of inquiry and open the door to a broader spectrum of possibilities regarding the role that dark matter and other unknown factors might play in the grand construction of the cosmos. As scientists continue to delve deeper into these mysteries, the ultimate goal is to piece together a fuller, more nuanced picture of the universe's vast diversity. This exploration promises to enhance our understanding of how galaxies, both typical and ultra-diffuse, evolve, interact, and contribute to the cosmic landscape we observe today. The concept of the multiverse theory, although speculative, has become one of the most captivating and mind-bending ideas in modern cosmology. The theory suggests that our universe, with all its intricate beauty and complexity, may not be the only one. In fact, it may be just one among countless others in an infinite expanse of universes, all coexisting side by side. Recent breakthroughs in cosmological research have reignited this notion, prompting serious discussions on the nature of reality itself. One intriguing aspect of this theory is the suggestion that all these parallel universes could have originated from the same fundamental fabric of existence. Governed by similar physical laws, these universes would still manifest with unique characteristics. For example, while our universe is capable of supporting life as we know it, other universes might host entirely different forms of life, or none at all. In some, the laws of physics could vary in ways that produce entirely different realities, where perhaps time flows differently, or the fundamental constants of nature take on alternative values. This vast diversity in the multiverse implies that there may be a plethora of possible realities, each as real as our own, but radically different in their nature. Support for the multiverse theory also comes from observations related to cosmic inflation. Cosmic inflation refers to a period of rapid and exponential expansion of the universe immediately following the Big Bang. Some scientists suggest that this expansion may have led to the creation of bubbles of spacetime, each bubble potentially evolving into its own universe, separated from the others by a boundary beyond our perception. If we could uncover traces of these bubbles, perhaps through variations in cosmic background radiation, it would lend substantial weight to the idea that our universe is merely one bubble in an incredibly vast multiverse. The implications of the multiverse theory stretch beyond the realms of physics, encouraging us to reconsider our place in the cosmos. As scientists investigate further, they are forced to confront fundamental questions about existence and our role within the grand narrative of reality. Could we be part of something far more expansive than we have ever dared imagine? The potential for endless variations of existence offers a provocative new lens through which to explore the nature of reality, encouraging us to rethink everything from the origins of life to the very fabric of the cosmos itself. Amidst these cosmic revelations, the idea of time travel through wormholes provides another tantalizing possibility. To grasp this idea, one must first understand the vast, interconnected nature of space-time. Picture space-time as an enormous piece of fabric, where space and time are not distinct entities but deeply woven together. In this fabric, massive objects such as stars and planets exert their gravitational pull, curving the very space-time around them. Wormholes are theoretical tunnels through this fabric, created by intense distortions in space-time that connect two distant points, both in space and time. If such wormholes exist, they would provide a shortcut, allowing for travel not just across vast distances in space, but also across different points in time. This challenges the very notion of linear time that we experience. Rather than time flowing steadily in one direction, as we intuitively perceive, wormholes open the possibility of traveling backward or jumping forward in time. This concept stems from Einstein's theory of relativity, which posits that massive objects can warp space-time. In extreme cases, this warping could potentially create bridges between distant locations, leading to the possibility of traveling through time as easily as we travel through space. While the existence of wormholes remains speculative, they offer a fascinating perspective on how time and space might operate on a deeper level, reshaping our fundamental understanding of the universe and the boundaries of reality. However, the notion of utilizing wormholes for time travel is far from simple and is fraught with significant complications. For starters, wormholes remain purely theoretical, their existence as yet unproven and never directly observed. In the realm of physics, while the mathematical equations suggest they could exist, no empirical evidence has yet confirmed their reality. This leaves us with a tantalizing possibility, but little more than speculation. Moreover, even if wormholes could be real, they would require exotic matter with negative energy to maintain their stability. Such matter, which has never been created or discovered, is essential for keeping a wormhole open long enough for any object, or even a person, to pass through. Without this exotic matter, a wormhole would collapse in an instant, essentially rendering time travel through this medium impossible. This challenge alone raises profound questions about the fundamental principles of physics and the limits of our technological capabilities. Beyond these technical hurdles, the very concept of wormholes brings into sharp focus the complexities surrounding causality, the cause and effect relationships that underpin our understanding of events. Time travel, even in its most theoretical form, could unravel the fabric of causality, potentially opening a Pandora's box of paradoxes. If one could alter events in the past, the effects on the present might be unpredictable, leading to alternate timelines or realities that defy logical understanding. These theoretical quandaries compel us to reconsider our most basic concepts. If time travel were indeed possible, it would upend our perceptions of history, fate, and the universe itself. Time would no longer be viewed as a one-way progression from past to present to future, but rather as a dynamic, multi-dimensional landscape. It would be a realm with countless possible paths, each one branching into its own version of reality. The very act of moving through time could fracture the continuity of history, allowing multiple realities to coexist, each with its own set of outcomes and consequences. Such ideas push us to not only contemplate the mechanics of time travel, but also its philosophical implications. The mere thought of wormholes forces us to reconsider the fluidity of time, suggesting that our understanding of the universe might be far more complex than we currently realize. In a world where time is not a fixed arrow, but a vast network of interconnected threads, our place in the cosmos might be far more fluid than we ever imagined. The concept of parallel universes has similarly captivated the minds of scientists and philosophers for generations, offering a rich vein of thought that challenges our understanding of reality itself. These parallel worlds are not merely the stuff of science fiction, but are increasingly taken seriously in theoretical physics, especially as advances in quantum mechanics, string theory, and the idea of a cosmic multiverse have opened new possibilities. One of the most significant contributions to our understanding of parallel universes comes from quantum mechanics, specifically the many worlds interpretation. This theory posits that every possible outcome of a quantum event occurs, not just in our own universe, but in its own separate parallel universe. For example, imagine flipping a coin. Rather than landing on heads or tails, the coin's flip results in two distinct outcomes. One universe where the coin lands heads up, and another where it lands tails. This interpretation suggests that every decision or quantum event, no matter how small, spawns a new universe, each one just as real as the last. It's a radical idea, one that challenges our concept of choice and free will, as it implies that all outcomes exist simultaneously, unfolding in an ever-expanding web of alternate realities. In addition to the quantum view, string theory offers another fascinating perspective on the multiverse. String theory, which proposes that the most fundamental particles in the universe are not point-like objects, but tiny, vibrating strings, introduces the possibility that our universe is just one of many, all vibrating at different frequencies. These parallel universes, hidden from our view, might have their own unique physical laws and constants, potentially allowing for entirely different types of life, matter, and environments. The theory suggests that our three-dimensional universe could be one slice of a far larger multi-dimensional reality, where countless other universes exist in parallel, each with its own distinct characteristics. These groundbreaking theories reshape not only our understanding of the universe, but also our concept of existence itself. The very fabric of reality seems far more intricate, interconnected, and bizarre than we could have ever imagined. The existence of parallel universes suggests that what we perceive as our reality may only be one of an infinite number of possibilities, each one shaped by the decisions and events that occur within it. The implications of such ideas stretch far beyond science, reaching deep into the realms of philosophy. Are we simply one version of ourselves, scattered across an infinite multiverse, each one experiencing a slightly different version of events? What does this mean for our sense of self, free will, and the nature of destiny? As research in these areas continues to unfold, our understanding of the multiverse grows ever more sophisticated. With each new breakthrough, the line between science fiction and science fact becomes increasingly blurred. The journey into parallel universes is still in its early stages, but the possibilities are endless. As we continue to peel back the layers of reality, it is impossible to predict where this exploration will take us, but the insights we gain could profoundly reshape our understanding of existence itself. Quantum entanglement is another phenomenon within quantum mechanics that continues to fascinate scientists and challenge our understanding of the universe. At its core, entanglement defies the conventional notion of locality, the idea that objects can only influence one another if they are in close proximity. In classical physics, an event occurring in one place should not instantly affect something far away. But quantum entanglement reveals that particles can become entangled, such that the state of one particle is directly linked to the state of another, no matter the distance between them. This seemingly magical connection between distant particles has been confirmed in numerous experiments, but its implications go far beyond the laboratory. On a cosmic scale, quantum entanglement raises profound questions about the interconnectedness of the universe. Could it be that the entire cosmos is, in some sense, entangled with distant stars, galaxies, and even entire regions of space-time influencing one another in ways we cannot yet fully understand? These revelations are just the beginning of what could be a revolutionary shift in our understanding of the universe. As we continue to explore the strange and mysterious world of quantum mechanics, the boundaries of what we know and what we thought was possible are pushed further and further. Whether wormholes, parallel universes, or quantum entanglement, the challenges and opportunities presented by these phenomena will shape the future of physics and our understanding of reality itself. However, entangled particles seem to defy conventional notions of space and time, presenting a puzzle that challenges our fundamental understanding of the universe. When two particles become entangled, they share a quantum state that transcends distance. Regardless of how far apart they are, whether just a few meters or light years distant, if something happens to one particle, the other will respond instantaneously. This response occurs faster than any signal could travel through space, raising profound questions about the nature of information, influence, and the very fabric of reality itself. What does it mean for our understanding of the universe if such connections can exist without any conventional force traveling through space? This phenomenon has been observed across vast distances, with experiments involving entangled particles over several kilometers and even across cosmic scales. These groundbreaking observations push the boundaries of our scientific knowledge and suggest that the universe might be far more interconnected than we can perceive with our senses. Entanglement challenges the classical idea that nothing can travel faster than light, opening the door to new theories about how information could potentially travel across the cosmos. The implications of quantum entanglement extend far beyond mere intellectual curiosity. They have the power to reshape the very foundations of physics. If locality, the idea that objects can only be influenced by their immediate surroundings, is not as rigid as once thought, it could force us to rethink space and time themselves. The instantaneous connection between entangled particles might point to a more holistic view of reality, one where everything is more deeply interconnected than we ever imagined. Such insights could revolutionize how we think about space, time, and even the fundamental forces of nature that govern the universe. Time dilation, a fascinating aspect of Einstein's theory of relativity, adds another layer of complexity to our understanding of reality. Time dilation occurs when time flows at different rates depending on the strength of a gravitational field. In regions of intense gravity, such as near a black hole, time slows down compared to weaker gravitational areas. This surprising behavior has profound implications for our understanding of the cosmos and the passage of time itself. For example, an observer near a black hole would experience time moving much more slowly than someone far away. While only a few minutes might pass for the person close to the black hole, hours or even years could elapse for someone observing from a distance. This phenomenon forces us to confront our intuitive understanding of time and raises difficult questions about the true nature of reality. Time, it seems, is not as fixed and universal as we once believed. The effects of time dilation also have real-world consequences for space exploration. For astronauts traveling at high velocities or near massive celestial objects, time would pass differently relative to people on Earth. Upon returning, they might find that their biological clocks have slowed, meaning they've aged less than those who stayed behind. This discovery forces us to reconsider our assumptions about aging, lifespan, and the very nature of time as we venture into the cosmos. Beyond these personal implications, time dilation also plays a critical role in the larger structure of the universe. By understanding how time behaves in varying gravitational fields, astronomers can better interpret the movements of galaxies, the behavior of stars, and even the expansion of the universe itself. As we dive deeper into the mysteries of space, these phenomena challenge our traditional narratives and expand our comprehension of the universe's intricate workings. Meanwhile, the icy geysers found on moons like Enceladus and Europa are offering us astonishing new insights into the conditions of distant worlds, revealing that the potential for life in the solar system may be greater than we thought. Enceladus, one of Saturn's smallest moons, has surprised scientists with its plumes of water vapor and ice particles that shoot into space from fissures in its icy surface. These geysers have opened up the exciting possibility of a subsurface ocean beneath the thick icy shell, creating an environment that could potentially harbor life. Even more remarkable is the discovery that the ice plumes contain organic molecules, evidence of chemical interactions between the ocean and the moon's rocky core. This raises fascinating questions about the potential for life in these extreme conditions. Enceladus, far from being a frozen relic of the past, is a dynamic world that could be home to complex biological processes. Europa, one of Jupiter's largest moons, presents similar mysteries. The evidence for a vast ocean beneath its frozen surface, coupled with signs of geological activity such as possible geysers or cryovolcanic eruptions, suggests that Europa is an active world with the potential to support life. If Europa's plumes resemble those found on Enceladus, it would further solidify the moon's role as a key player in the search for extraterrestrial life. The discovery that both of these moons may harbor subsurface oceans has transformed our understanding of where and how life could exist beyond Earth. These moons, once seen as distant and unremarkable, are now central to our quest to understand the broader dynamics of life in the cosmos. These icy geysers are not just a scientific curiosity, they are the key to unlocking the mysteries of the solar system. They suggest that even in the coldest corners of space, life's building blocks could be present, waiting for us to discover them. These findings remind us that the universe is far more dynamic and complex than we ever imagined, and there is much more to explore in the cold, distant reaches of space. Closer to home, the surface of Venus challenges our traditional ideas about habitability. Once considered a potential sister planet to Earth, Venus has revealed itself to be an unforgiving and hostile world. Its thick atmosphere, composed mostly of carbon dioxide, exerts a pressure more than 90 times that of Earth's surface. This oppressive atmosphere traps heat, raising surface temperatures to a blistering 430 degrees Celsius, hot enough to melt lead. These extreme conditions force us to reconsider what makes a planet habitable and what life could thrive under such unforgiving circumstances. The harsh environment of Venus presents an interesting paradox. While Venus may not support life as we know it, studying its extreme conditions forces us to rethink the fundamental ingredients that define habitability. Could life exist in environments that seem, at first glance, too hostile to sustain anything? The exploration of Venus, along with the study of icy moons like Enceladus and Europa, continues to push the limits of our imagination and challenges our assumptions about the nature of life in the universe. As we venture deeper into space, the line between the possible and impossible becomes ever more blurred, expanding the horizons of what we consider to be the conditions necessary for life. However, if a planet like Venus, similar in size and proximity to the Sun, can develop such inhospitable conditions, it raises crucial questions about the very nature of life itself. Could life survive in environments vastly different from our own? Could it adapt to extreme pressures, scorching temperatures, or even corrosive atmospheres? These questions force us to reconsider our assumptions about life beyond Earth. What if life isn't bound by the conditions we typically associate with livable worlds? Microbial life, for example, has been discovered thriving in some of the harshest corners of our own planet, places like hot springs and deep ocean vents. These discoveries suggest that life might not need the same cozy, Earth-like conditions we consider essential. And as we look to Venus, with its thick, toxic atmosphere and surface temperatures hot enough to melt lead, we are reminded that we may need to expand our criteria for what constitutes a habitable environment. Venus serves as a case study in the complexity of planetary evolution and climate dynamics. It reveals a deeper, more intricate narrative than we could have imagined, a cosmic perspective that compels us to think beyond the familiar conditions of Earth. In fact, the planet's extreme environment underscores the diversity of conditions that might exist elsewhere in the universe, potentially supporting forms of life that are beyond our current understanding. This exploration pushes us to reconsider the very foundation of life itself. Could life exist in places with temperatures hundreds of degrees higher than those on Earth? Or in atmospheres thick with sulfuric acid? These questions open the door to a broader range of possibilities for extraterrestrial life, challenging us to rethink what it means to be alive and where life might arise in the vast cosmos. As we continue to probe the depths of these questions, we embark on a journey that transforms our understanding of life's potential forms and its ability to adapt. Our assumptions about what constitutes a habitable world are shifting as we recognize that the universe may host life in places we never thought to look. Whether on Venus or beyond, this search invites us to imagine new possibilities, driving us to expand our vision of life's potential across the cosmos. Meanwhile, Mars has become a treasure trove of geological features that challenge everything we thought we knew about the planet. Once believed to be a barren, frozen wasteland, Mars is now revealing evidence of a dynamic history far more complex than previously imagined. Through extensive observations, scientists have identified gigantic channels and ancient riverbeds, hinting at the possibility that Mars may have hosted flowing water long after the planet's formation. These findings suggest that Mars could have once supported a vibrant, watery environment, a far cry from the dry, desolate surface we see today. One of the most compelling discoveries on Mars involves the northern plains, where vast ice deposits appear to have been shaped by glaciers. These formations are strikingly similar to those found in glacial regions on Earth, suggesting that Mars experienced significant glacial activity in the distant past. This realization proposes that Mars was not only home to liquid water, but may have also gone through ice ages and dramatic climate changes, transforming its surface in ways that we are only beginning to understand. Current models of Martian geology paint a picture of a planet with a far more nuanced climate history. Mars was not always the cold, lifeless world we see today, but rather a place of dynamic climatic shifts, periods of warmth followed by cold, with alternating cycles that might have radically altered its surface. Additionally, the massive volcano Olympus Mons, the tallest volcano in the solar system, provides further evidence of Mars's volcanic activity in the past. This enormous shield volcano speaks to a time when volcanic processes were far more active than scientists had previously assumed. In fact, Mars's tectonic features, including rift valleys and faults, suggest that the planet may have experienced tectonic stresses similar to those on Earth. These geological marvels invite us to reconsider the idea that Mars was once a static, lifeless world. Instead, it might have been shaped by complex geological processes over millions of years, processes that could have played a role in supporting life. Each new discovery on Mars fuels our curiosity, challenging long-held assumptions and prompting us to reconsider what the planet might have been like in its early history. More importantly, it urges us to ask whether Mars could still harbor life beneath its harsh exterior. As we continue to explore Mars, we uncover remnants of a world that might have been capable of sustaining life, and, just maybe, could still do so today. Saturn's rings, one of the most visually captivating features in our solar system, are more than just a beautiful spectacle. Composed of countless particles ranging from tiny ice grains to massive chunks of ice and rock, the rings present an intricate structure that invites both scientific intrigue and aesthetic admiration. These rings, characterized by bright and dark bands, varying thicknesses, and diverse compositions, raise profound questions about the longevity and evolution of planetary ring systems throughout the universe. One of the most striking aspects of Saturn's rings is their youth in cosmic terms. Though they appear magnificent, many scientists believe that Saturn's rings may have formed relatively recently, just a few 100 million years ago. This raises an important question. How long can such rings endure? What keeps them intact in the face of countless forces at work? The answer lies in understanding the dynamic processes shaping these rings. Saturn's gravity, the constant interaction between ring particles, and external influences, such as meteoroid impacts or tidal forces from Saturn's moons, all play significant roles in the ring's lifespan. Despite their grandeur, Saturn's rings face constant wear and tear. The particles that make up the rings are in a perpetual state of collision. These collisions lead to the gradual erosion of the ring material, with some particles drifting into Saturn's atmosphere or coalescing into larger bodies. Over time, this erosion could cause the entire ring system to dissipate, perhaps within a few hundred million years, much shorter than the lifespan of the planet itself. This dynamic process prompts fascinating questions about the origins and eventual fate of planetary rings. By comparing Saturn's rings to those of other gas giants like Jupiter, Uranus, and Neptune, scientists are beginning to explore how different environments and histories influence the formation and longevity of these structures. Some of these planets have faint, fleeting rings, while Saturn's rings stand as a magnificent yet temporary feature. The study of Saturn's rings is more than just an aesthetic exercise. It provides valuable insights into the forces that shape celestial bodies. Through this research, we are not only unraveling the mysteries of Saturn itself, but gaining a deeper understanding of the processes that govern the evolution of planetary systems. In doing so, we are invited to ponder the fate of other ring systems in the universe and what these structures reveal about the forces that mold the cosmos. In the rapidly evolving field of exoplanet research, scientists have recently made groundbreaking strides in understanding the interiors of distant worlds. With the discovery of thousands of exoplanets, the focus has now shifted to what lies beneath the surfaces of these far-flung bodies. By analyzing the mass, size, and density of exoplanets, researchers are piecing together a picture of their potential compositions and geological activity, insights that are crucial for understanding whether these planets could support life. Traditionally, we have used Earth as the benchmark for habitability. Its mix of liquid water, an atmosphere, and a stable climate has made it the gold standard in the search for life. But as our exploration of exoplanets deepens, it becomes clear that other planets may not need to resemble Earth to support life. Instead, we are beginning to recognize that a planet's interior, its composition, internal heat, and geological processes can play a pivotal role in determining whether life could arise. By examining the composition and activity beneath the surface of exoplanets, scientists are refining their criteria for habitable worlds. This research is reshaping our understanding of what makes a planet capable of supporting life. We are learning that habitability may not be confined to Earth-like conditions, but could extend to environments we had never before considered. However, studies suggest that the potential environments of exoplanets are far more varied than previously thought, painting a much broader picture of what could exist beyond our solar system. Some exoplanets, for instance, may be dominated by vast oceans of water, while others may be enshrouded in thick atmospheres laden with gases such as hydrogen or helium. The sheer diversity of these compositions sets the stage for a wide array of surface conditions and geological processes that could radically shape the evolution of their climates. Recent findings indicate that planets with abundant water and volcanic activity could create the necessary chemical diversity for life, similar to the conditions that may have existed on early Earth. Moreover, technological breakthroughs in telescope design have allowed scientists to peer deeper into the atmospheres of these distant worlds. The presence of gases like oxygen and methane in an exoplanet's atmosphere, for example, can point to biological processes hinting at the possibility of life. Yet, even more astonishingly, research has shown that seemingly inhospitable environments might harbor unexpected potential for life. Planets enduring extreme pressures and temperatures, for instance, may still host microbial life thriving in subsurface oceans or within their rocky mantles, where the conditions differ vastly from the hostile surfaces above. In this growing understanding of exoplanetary interiors, our view of what constitutes a habitable environment has expanded dramatically. It's becoming clear that life may not merely be a product of adaptation to familiar conditions, but could potentially emerge in ways and places we never imagined. This evolving knowledge is changing the way we think about the universe and spurring our curiosity to explore how life might manifest in forms we cannot yet comprehend. As we continue to unravel the mysteries of exoplanets, we move closer to realizing the full range of possibilities that may exist in the cosmos, waiting to be discovered among the stars. In a similar vein, recent observations of supernovae have fundamentally altered our understanding of how stars are born, live, and die, particularly shedding new light on the diversity of these explosive events. For centuries, scientists believed that supernovae were primarily caused by the death throes of massive stars that had exhausted their nuclear fuel. However, new data from modern observations paints a far more intricate picture, suggesting that even stars once thought to be stable or of lower mass can produce supernovae. This revelation has led scientists to reassess the mechanisms behind these cosmic explosions, revealing that the processes leading to a star's violent end are far more varied than previously believed. One of the most striking discoveries in this regard comes from the study of a specific type of supernova known as Type A. Traditionally, these explosions were thought to result from the detonation of white dwarfs, stellar remnants that have shed their outer layers. It was believed that such white dwarfs could only explode once they reached a critical mass by accumulating material from a companion star. Yet, new findings suggest that other mechanisms could trigger these explosive events, such as the merger of two white dwarfs. This has far-reaching implications, expanding the range of circumstances under which supernovae might occur and, in turn, reshaping our understanding of stellar evolution. In addition to these groundbreaking revelations, advanced telescopic observations have uncovered an astonishing variety of supernovae, with some proving to be more energetic and lasting longer than traditional models would predict, while others dim far more quickly than expected. These variations hint at the complexity of stellar behavior and suggest that our current models do not fully capture the diversity of stellar phenomena. The implications are profound, offering a glimpse into the many factors, ranging from the star's environment and rotation rates to its chemical composition, that can influence its ultimate fate. As astronomers continue to gather data from state-of-the-art observatories, our understanding of supernovae and the life cycles of stars evolves with every new discovery, refining our knowledge of the universe's history and the formation of the elements. The ongoing journey to understand these cosmic events serves not only as a source of intellectual inspiration, but also as a reminder of the vastness of what remains unknown about the universe. Each new breakthrough in supernova research opens a door to more questions and greater awe, as it underscores how much more we have yet to learn about the intricacies of star life cycles. One of the most significant milestones in modern astrophysics came with the detection of an electromagnetic counterpart to gravitational waves from a neutron star merger, an event designated GW170817. This groundbreaking discovery not only confirmed long-standing theories about the origins of heavy elements, but also ushered in a new era of multi-messenger astronomy. This emerging field combines different types of signals, gravitational waves and electromagnetic radiation, to deepen our understanding of cosmic phenomena. When two neutron stars collide, they send ripples through space-time, which we can detect as gravitational waves here on Earth. Following the detection of these waves, astronomers turned their telescopes to the location in the sky where the event occurred, seeking the electromagnetic counterpart, a burst of light known as a kilonova. This sudden burst of energy was far brighter than typical nova events, and it manifested across the entire electromagnetic spectrum, from gamma rays to optical light. This burst of brilliance provided strong evidence that neutron star mergers are indeed responsible for the creation of some of the universe's heaviest elements, including gold and platinum. Within hours of the gravitational wave detection, telescopes around the world focused on the event's location, gathering data on the kilonova explosion as well as its afterglow, which continued to evolve and persist over time. This joint observational effort produced a wealth of information, revealing how neutron star mergers contribute uniquely to the elemental makeup of the universe. It also provided insights into the physical conditions that prevail during and after such cataclysmic events. The data not only reinforced our understanding of the origin of heavy elements, but also added depth to our knowledge of the fundamental processes driving the formation and evolution of the cosmos. Furthermore, the groundbreaking success of this multi-messenger approach has ignited tremendous excitement within the scientific community, propelling future astronomical endeavors into new realms of possibility. This approach, which combines the observation of gravitational waves with electromagnetic signals, has shown that such observations could reveal critical secrets about the universe's most extreme and violent phenomena. The knowledge gained from observing the merger of neutron stars has provided an unprecedented opportunity for scientists to delve into the life cycles of stars, the formation of the elements, and even the very fabric of the universe itself. Gamma-ray bursts, GRBs, some of the universe's most intense explosions, release an extraordinary amount of energy in the form of gamma rays. These bursts can temporarily outshine entire galaxies, making them the most luminous events we observe in the cosmos. GRBs are often tied to catastrophic cosmic events, such as the collapse of massive stars or the collision and merger of neutron stars. Through the study of these bursts, scientists are able to glean valuable insights into the powerful processes at work in the universe, providing deeper understandings that have shaped cosmic evolution over time. The intense light emitted by gamma-ray bursts serves as a cosmic beacon, enabling astronomers to observe and analyze these events across vast distances. These bursts can vary dramatically in duration, from a mere few milliseconds to several minutes. Short bursts, typically associated with the death throes of massive stars, are indicative of rapid and violent events, while longer bursts, often linked to neutron star mergers, suggest more prolonged and complex processes at play. This variability in duration helps scientists categorize different types of GRBs, offering clues into the underlying mechanisms that drive their extraordinary energy production. Moreover, gamma-ray bursts act as invaluable beacons, illuminating the surrounding universe in ways that go far beyond the explosion itself. The afterglow of a burst, its residual light, provides researchers with vital data not only about the explosion's characteristics, but also about the environment in which it occurred. By studying the afterglow, scientists can deduce the composition and structure of distant galaxies, offering a glimpse into their formation and evolution. These cosmic fireworks enable astronomers to probe the very early universe, giving us a better understanding of its infancy and subsequent development. In essence, gamma-ray bursts are not just fascinating phenomena, they are central to unraveling the mysteries of the cosmos. As astronomers continue to observe and analyze these events, they deepen our understanding of some of the most energetic processes in existence, offering insights that connect the distant past of the universe with its present state. Each burst is like a fleeting flash of light in the vast darkness of space, revealing the profound complexity and dynamism of the universe. The study of cosmic inflation has uncovered astonishing revelations that challenge and expand our understanding of the Big Bang. First proposed in the early 1980s, the theory of inflation suggests that in the split second following the Big Bang, the universe expanded at an exponential rate. This rapid growth not only explained several cosmic puzzles, such as the uniformity of the cosmic microwave background, CMB, radiation, but it also resolved questions about how distant regions of the universe could have such similar temperatures and densities, despite being separated by vast distances. One of the most startling revelations of the inflation theory is that it paints a picture of the early universe as far more complex than we had previously imagined. Rather than a smooth and uniform expansion, inflation suggests that the universe underwent rapid fluctuations, resulting in regions of varying densities. These tiny quantum fluctuations eventually gave rise to the vast cosmic structures we observe today, galaxies and galaxy clusters. This transition from the quantum scale to the macroscopic structure of the universe underscores the profound significance of that incredibly brief moment of inflation. It was during this fleeting period that the seeds of the universe's structure were sown. Furthermore, the concept of inflation introduces the possibility that our universe might not be unique. Some theories propose that inflation could be a recurring event, leading to the creation of a multiverse, an ensemble of distinct universes, each potentially governed by different physical laws or constants. This hypothesis pushes the boundaries of our understanding, challenging our perception of reality and raising profound questions about the very nature of existence. The notion that the universe we inhabit could be just one of many, each with its own unique properties, forces us to reconsider our place in the cosmos. In the grand scheme, cosmic inflation doesn't merely enhance the Big Bang theory, it transforms it. It invites us not only to reconsider the origins of our universe, but also to speculate about what might lie beyond it. Each new revelation drawn from the study of inflation carries with it exhilarating implications, reminding us that the quest to understand the universe is an ever-expanding horizon, teeming with mysteries yet to be uncovered. Meanwhile, cosmic voids, those enormous expanses of space that contain very few galaxies, have recently emerged as key elements in our understanding of the universe's composition. Historically, astronomers considered these voids to be nothing more than empty spaces, mere gaps between the galaxies. However, ongoing research suggests that these voids may hold crucial clues about the structure and evolution of the universe itself. Far from being insignificant, they may represent the vast, unseen infrastructure that supports the cosmic web, connecting the galaxies in intricate and unexpected ways. As our tools and observational techniques continue to improve, the study of these enigmatic voids may reveal even more secrets about the true nature of our universe. Recent studies have revealed that cosmic voids, once thought to be mere empty spaces, actually offer a profound window into the universe's hidden mechanisms. Far from being devoid of significance, these vast expanses of emptiness provide unique insights into the distribution of matter, the influence of dark energy, and the very structure of the cosmos. Through careful observation and analysis, scientists have uncovered that the characteristics of these voids are key to understanding the effects of dark energy on the universe. Dark energy, an enigmatic force that makes up about 70% of the universe's total energy content, is responsible for driving the accelerated expansion of the cosmos. By examining the size, shape, and density of cosmic voids, researchers can uncover how dark energy interacts with the matter around it. These investigations have shown that voids are not only larger than previously expected, but also more elongated, challenging our earlier understanding of the very fabric of space-time itself. This shift in perspective suggests that cosmic voids play a far more significant role in the evolution of the universe than once thought. In addition to their role in dark energy studies, cosmic voids are now believed to influence the formation and development of galaxies. Galaxies tend to form at the edges of these voids, where the gravitational forces from surrounding matter pull gas and dust together to create stars and stellar systems. This phenomenon has led to the discovery of distinct patterns in the distribution of galaxies, often aligning in ways that follow the contours of cosmic voids. By studying these formations, scientists are able to trace the history of galaxy formation and better understand how the universe has evolved over billions of years. As we continue to redefine our understanding of these vast, seemingly empty spaces, it is becoming increasingly clear that cosmic voids are a fundamental component of the universe's structure. They offer us valuable clues about the interplay between dark matter and dark energy, providing a richer and more complex picture of the universe's past, present, and future. These studies are not just filling in gaps in our knowledge. They are revolutionizing our very understanding of the cosmos itself, shedding light on the intricate forces that govern everything from the smallest particles to the largest galactic structures. In our quest to explore the mysteries of the universe, one of the most striking phenomena we encounter is the movement of distant galaxies. As we peer into the depths of space, we observe galaxies racing away from us, their light shifting toward longer, redder wavelengths. This redshift, a telltale sign of the universe's expansion, has been one of the cornerstones of modern cosmology. However, the speeds at which these galaxies are moving often exceed what we would expect based on traditional models of gravity and dark matter. These unexpected velocities raise intriguing questions about the forces at work in the universe. One of the most fascinating aspects of these anomalies is their potential connection to dark energy. While much of the universe's mass is visible to us through stars, planets, and other celestial objects, a substantial portion remains hidden. Dark energy, which is thought to account for approximately 70% of the universe's energy content, is believed to be driving the accelerated expansion of the universe. This mysterious, repulsive force could help explain why galaxies are receding from one another at such high speeds, faster than gravity alone would predict. Adding to the intrigue, researchers have observed variations in the velocities of galaxy clusters. These discrepancies suggest that gravitational interactions between clusters may be more complex than our current models can fully explain. Some scientists speculate that this could point to the existence of unidentified forms of matter or energy, which could be influencing galactic motion in ways that are not yet understood. If these theories are confirmed, they could dramatically alter our understanding of the fundamental laws of the universe. As scientists continue to investigate these cosmic anomalies, they rely on advanced telescopes and expansive surveys to gather more data. Each new discovery adds a piece to the puzzle, bringing us closer to a comprehensive understanding of the universe's composition and the forces that shape it. The ongoing quest for knowledge serves as a reminder that even with all of our technological advancements, the cosmos still holds many secrets, waiting to be uncovered. One particularly fascinating class of objects that has captured the attention of astrophysicists is pulsars. These incredibly dense remnants of supernova explosions are some of the most intriguing objects in the universe. Pulsars are rapidly rotating neutron stars, emitting beams of radiation from their magnetic poles. While their behavior and characteristics have been studied for decades, they continue to captivate scientists with their unusual properties. Perhaps one of the most striking features of pulsars is their astonishing rotational speed. Some pulsars rotate so rapidly that they complete a full revolution in a fraction of a second. This extreme rotation presents a unique challenge for physicists who seek to understand the forces at play within these extraordinary objects. The rapid spinning raises important questions about the nature of matter under such extreme conditions, especially when combined with the pulsar's extraordinary density. A typical pulsar can contain more mass than the Sun, yet it is compressed into a sphere no larger than a city. This immense density suggests the presence of matter that behaves in ways we cannot observe on Earth. Many physicists hypothesize that the core of a pulsar may harbor exotic forms of matter, such as quark matter. This hypothetical substance exists under conditions where neutrons break down into their fundamental components, quarks. Studying these phenomena is a reminder that the universe often operates on principles that defy our everyday understanding of physics. In addition to their rapid rotation and extreme density, pulsars also exhibit phenomena that offer further insights into their inner workings. One of the most intriguing is the occurrence of glitches in their spin rates. These sudden changes in rotational speed suggest that something is disrupting the pulsar's internal mechanics. Scientists believe these glitches may be caused by interactions with exotic forms of matter, potentially reshaping our understanding of how pulsars behave and function. These glitches raise new questions about how matter behaves under the immense gravitational and density conditions found within neutron stars, conditions that are beyond our ability to replicate on Earth. As researchers continue to study these cosmic enigmas, they are gradually piecing together a more complete picture of the universe's most extreme environments. Pulsars, along with other exotic objects like black holes and cosmic voids, are pushing the boundaries of what we know, offering glimpses into a cosmos that is far stranger and more complex than we ever imagined. Magnetic fields generated by pulsars have long been a subject of intense curiosity and study. Pulsars, the remnants of massive stars that have exploded into supernovae, are not just fascinating because of their intense gravitational fields, but also because of their magnetic properties. Some pulsars exhibit magnetic fields that are far stronger than anything we can create in laboratories here on Earth. These magnetic fields are so extreme that they can warp space-time itself, creating environments where exotic forms of matter might exist. Matter with properties that we are only beginning to understand. This strong magnetism is one of the most mysterious aspects of pulsars. It's believed that the intense magnetic fields could be influenced by forms of matter that don't behave in ways we can easily observe or replicate. These so-called exotic materials, which might be present deep within pulsars, could challenge our current ideas about physics and matter. The more we learn about pulsars, the more they seem to offer a glimpse into the most fundamental forces of the universe, unlocking possibilities that could revolutionize our understanding of space, time, and matter itself. In the realm of cosmic exploration, the discovery of new asteroid belts in distant solar systems has sparked a rethinking of how we understand the formation of planetary systems. Traditionally, we have envisioned solar systems forming in relatively uniform ways, planets and other celestial bodies emerging in predictable patterns from a rotating disk of gas and dust. However, recent findings have thrown this neat, predictable model into question. New asteroid belts observed around distant stars suggest that the process of solar system formation may be far more complex and variable than we initially thought. Asteroid belts are often remnants of material that never coalesced into planets, yet they may hold clues to the various factors that influence planetary formation. These factors could include gravitational interactions with large planets, the dynamics of gas and dust, and the way in which energy is distributed throughout a forming solar system. Some of these asteroid belts are found in surprising locations, orbiting at unexpected distances from their parent stars. This discovery challenges long-held assumptions about the relationship between the temperature of a star and the location of orbiting bodies. Rather than a straightforward connection between a planet's location and the temperature of its environment, these findings suggest that material can accumulate and persist in regions we hadn't anticipated. The implications of this discovery are profound. It suggests that the formation of planetary systems could follow many different paths, influenced by a variety of factors that lead to distinct, sometimes unpredictable outcomes. Each solar system could be the result of a unique set of conditions, events, and forces at play. By studying distant asteroid belts, scientists not only gain a better understanding of solar systems far from our own, but they are also learning more about the processes that may have shaped our own cosmic neighborhood. This new perspective on solar system formation challenges the idea that there's a one-size-fits-all model for how planets and other celestial bodies come into existence. The research into distant asteroid belts also encourages a closer look at the history of our solar system. By comparing other solar systems to our own, we can uncover insights about the conditions that led to the formation of Earth, the inner planets, and even the distant icy bodies at the edges of our solar system. As we continue to explore these distant systems, we're uncovering new possibilities for how life could arise in diverse environments. This ongoing research fundamentally reshapes our understanding of the cosmos and our place within it. In a similarly fascinating vein, the study of exoplanets in extreme environments, particularly those that experience tidal locking, has led to groundbreaking insights into the potential for life beyond Earth. Tidal locking occurs when a planet's rotational period matches its orbital period around its star, leading to one side of the planet always facing the star while the other side remains in eternal darkness. This creates stark temperature differences between the two hemispheres. One side could be blisteringly hot while the other side plunges into frigid cold. Despite these extreme conditions, scientists have found that liquid water, a key ingredient for life as we know it, might still be able to exist in the narrow twilight zone between the hot and cold sides of the planet. In this region, temperatures could be more moderate, offering a stable environment where water could remain in liquid form. This twilight zone makes tidal-locked exoplanets particularly intriguing as potential habitats for life. The conditions in this zone raise the possibility that even in extreme environments, life, whether simple or complex, could find a way to thrive. Moreover, the planet's atmosphere plays a critical role in determining whether life can persist in these conditions. A thick atmosphere could help to redistribute heat from the sunlit side to the dark side, effectively mitigating the temperature extremes. If such conditions hold true, even planets with seemingly inhospitable environments might still support life, albeit possibly life forms very different from what we experience here on Earth. Astrobiologists, ever optimistic, continue to explore these possibilities, examining data from ongoing missions focused on exoplanets. Their research is transforming how we define habitability, opening new doors to finding life in places we previously thought to be too extreme. The study of these unique environments teaches us that life is incredibly adaptable, capable of surviving in conditions that we would never have imagined possible. In our own solar system, the discovery of potentially habitable moons has added another layer to our understanding of where life might exist beyond Earth. For years, our focus was primarily on planets like Mars, but recent findings have expanded the possibilities to moons such as Europa, Enceladus, and Titan. These moons present compelling environments that challenge traditional views on habitability. Europa, one of Jupiter's largest moons, is covered by a thick layer of ice, beneath which scientists believe there may be a vast ocean of liquid water. This icy shell insulates the ocean from the frigid space environment, raising the possibility that chemical reactions similar to those that occurred on early Earth might be taking place beneath the surface. Researchers are particularly intrigued by the idea that hydrothermal vents on Europa's ocean floor could provide the necessary energy and nutrients to support life, even in this dark and extreme environment. Similarly, Enceladus, a moon of Saturn, has been shown to eject plumes of water vapor into space, and these plumes contain organic molecules, key building blocks for life. This discovery suggests that beneath its icy crust, Enceladus might harbor a dynamic and complex environment capable of sustaining microbial life. These findings represent a dramatic shift in how we think about life beyond Earth. What was once considered the realm of science fiction is now the subject of serious scientific inquiry, as the potential for life in these hidden oceans is explored more deeply. The discoveries of these moons continue to challenge our assumptions about where life can exist. By expanding the boundaries of our search for life, scientists are pushing the frontiers of exploration, venturing into realms once thought to be inhospitable. These breakthroughs remind us that the universe is far more mysterious and full of possibility than we could have ever imagined. What we once thought was science fiction may soon become reality, as the search for life continues in the most unexpected corners of our solar system and beyond. Titan, one of Saturn's largest moons, presents a stunning, albeit vastly different, analogy to Earth. Its surface is unlike anything we know, with rivers and lakes not filled with water, but with liquid methane and ethane. These hydrocarbons flow and pool across Titan's vast landscapes, creating a bizarre yet fascinating environment. Despite the drastic differences in surface conditions when compared to Earth, Titan's chemical processes raise an exciting and provocative possibility: the existence of life forms that might use biochemistry is entirely alien to what we are familiar with. This notion challenges our traditional definitions of life, prompting us to reconsider the very conditions that are essential for life to thrive. The discoveries on Titan invite us to expand our search for life beyond Earth, pushing the boundaries of what we have ever imagined, and encouraging us to think outside the narrow constraints of terrestrial biology. This shift in perspective can be traced to our understanding of extremophiles, remarkable organisms on Earth that thrive in the harshest, most unforgiving environments. These organisms are not just survivors, they are pioneers, showing us that life can flourish in conditions once thought to be completely inhospitable. From extreme heat to freezing cold, from high radiation to acidic environments, extremophiles have been found in the most extreme places on our planet. Studying these resilient life forms has led scientists to appreciate the remarkable adaptability of life. These organisms have evolved to withstand environments that would obliterate most other living beings, and their existence raises critical questions about where life might survive elsewhere in the universe. If life can thrive in Earth's most hostile environments, such as the deep oceanic hydrothermal vents or the frozen deserts of Antarctica's dry valleys, then why couldn't it survive on distant planets or moons with similarly extreme conditions? Take Mars, for instance, with its frigid temperatures, thin atmosphere, and high levels of radiation. Or the icy moons of Jupiter and Saturn, like Europa and Enceladus, which are known to harbor subsurface oceans beneath their frozen crusts. Could these moons provide the necessary conditions for life, even if it's in a form we have yet to conceptualize? Extremophiles suggest that life might not only survive, but actually thrive in places we previously dismissed as completely uninhabitable. As our understanding of these resilient organisms deepens, it broadens the scope of where we should search for extraterrestrial life. It expands the search from the surface of planets to the hidden subterranean oceans beneath ice layers, and even to the clouds of distant, inhospitable atmospheres. If life can exist in Earth's most extreme environments, it seems reasonable to extend that possibility to other corners of the universe. The very existence of extremophiles serves as a testament to life's remarkable versatility and resilience. They show us that life is not just a fragile thread dependent on stable, familiar conditions, but a dynamic force capable of adapting and surviving in the most unexpected and even hostile scenarios. The discoveries of extremophiles thus play a pivotal role in driving humanity's search for life beyond Earth, igniting hope and curiosity. They inspire us to explore the farthest reaches of the cosmos with the belief that life's potential is far greater and more varied than we once imagined. Meanwhile, astronomical advancements have significantly deepened our understanding of exoplanets, planets that orbit stars beyond our solar system. With the development of powerful telescopes, scientists can now analyze the atmospheric composition of these distant worlds. This capability has profound implications for the search for extraterrestrial life. For the first time, we can detect gases in the atmospheres of exoplanets that might suggest biological activity, such as methane, oxygen, and carbon dioxide. These gases, commonly associated with life processes on Earth, provide tantalizing hints that certain exoplanets may harbor environments conducive to life. One of the most significant findings involves the detection of water vapor in the atmospheres of some exoplanets. Water, as we know, is essential for life as we understand it. The presence of this critical compound in the atmospheres of distant worlds brings the possibility of life even closer. Water's role as a solvent for biochemical reactions makes it a cornerstone for the kind of life we are most familiar with. Its presence in the harsh and distant reaches of the cosmos gives scientists hope that life, in some form, might exist on these faraway worlds. The study of these exoplanets, combined with the lessons learned from Earth's extremophiles, suggests that our universe may be teeming with possibilities for life that could take forms we have yet to imagine, existing in environments we have not yet begun to explore. In a world where our understanding of life is constantly evolving, these discoveries push the boundaries of what we consider possible, inviting us to rethink our place in the universe and the vast untapped potential for life that might exist beyond our home planet. The discovery of various gases in distant planetary atmospheres does more than merely hint at the potential for sustaining life. It opens up a vast array of scientific inquiries, each one progressively deepening the complexity of our understanding of exoplanets. For instance, while the presence of oxygen in an atmosphere could naturally arise from biological processes, scientists are also exploring alternative explanations for its existence. This duality in potential origins makes the search for life not just complex, but also profoundly fascinating. The question of whether exoplanets could host life has given rise to an entirely new field of study: astrobiology, a discipline focused on deciphering the myriad ways in which environments radically different from our own might support living organisms. As astronomers and astrobiologists peel back the layers of these distant worlds, they are pioneering innovative technologies and methods to assess habitability. One of the most exciting developments is the use of space-based missions that capture light filtering through the atmospheres of exoplanets. This light can be analyzed to reveal the chemical composition of the atmosphere, offering scientists a glimpse into the planet's potential to support life. Each new discovery about the chemical makeup of these alien atmospheres brings us closer to understanding what constitutes a habitable environment, adding another piece to the puzzle of life in the universe. As researchers piece together these atmospheric profiles, a sense of collective curiosity about the cosmos emerges. We are no longer simply observing distant stars and planets. We are actively investigating the possibility that the universe is home to life forms, both simple and complex. Each new finding sparks further questions about our place in the cosmos. Questions about whether we are alone or if, hidden somewhere among the stars, other forms of life are waiting to be discovered. The mystery of the universe extends far beyond the atmospheres of exoplanets. Humanity has long been captivated by the idea that we may not be alone in the cosmos, and our search for intelligent extraterrestrial life has taken many forms over the years. Among the most intriguing events in this search is the discovery of the so-called WOW signal in 1977. This powerful burst of radio waves was detected by astronomer Jerry R. Ehman while working on a SETI, Search for Extraterrestrial Intelligence project at Ohio State University. The signal's intensity and narrow-band nature made it seem like it could be artificial, yet it has never been detected again or identified since. Despite its elusive nature, the wow signal sparked the imaginations of scientists and enthusiasts alike, raising tantalizing possibilities about the existence of extraterrestrial civilizations. Alongside this mysterious signal, another perplexing phenomenon has captured the attention of astronomers: fast radio bursts, or FRBs. These brief but intensely powerful bursts of radio emissions last only milliseconds, yet they release an amount of energy equal to that of the sun's output over several days. Despite numerous theories, the origin of FRBs remains a subject of intense debate. Some scientists propose that these bursts are caused by neutron stars, while others speculate that they might be signals from advanced extraterrestrial technologies. Each new observation of FRBs challenges our assumptions and fuels our collective curiosity about what might lie beyond the boundaries of our solar system. The debate surrounding these bursts has opened new avenues for research into the nature of these enigmatic signals and whether they might indeed be evidence of extraterrestrial intelligence. In addition to these mysterious signals, the scientific community remains deeply engaged with other unexplained phenomena that might point to the existence of life beyond Earth. The recurring nature of FRBs, for instance, has sparked discussions about whether these signals could be communications from advanced civilizations elsewhere in the universe. These discussions are often framed by the Drake equation, a mathematical formula that estimates the number of communicative extraterrestrial civilizations in the Milky Way galaxy. Though our knowledge remains limited, the pursuit of evidence for extraterrestrial life is not just a scientific endeavor. It also fuels the imagination of people around the world. Every discovery, every breakthrough leads to new questions and new possibilities, prompting us to continue our search for answers. These perplexing signals remind us of our place in the vast, unexplored universe and continue to propel us forward in our quest for knowledge. Meanwhile, a recent discovery on Mars has added a new layer of excitement to the search for life beyond Earth. The identification of microbial fossils on the red planet has profoundly reshaped our understanding of Mars' history and its potential to have once harbored life. For years, scientists have speculated about whether Mars could have supported life, but the discovery of these fossils offers compelling evidence that microbial organisms may have indeed thrived in the planet's past. These fossils point to a time when Mars had a much warmer and wetter climate, conditions that would have been more hospitable to life. This discovery helps us visualize Mars not as the cold, barren desert we see today, but as a planet with a dynamic environment, possibly rich with life-supporting elements. The findings suggest that large bodies of liquid water may have existed on Mars in the distant past, and geological processes could have sustained microbial life for millions of years. Such revelations force us to reconsider Mars as a lifeless rock in space and instead see it as a once vibrant planet with the potential to support life. These findings also raise new questions about how life might arise on other planets under similar conditions, prompting us to consider the adaptability of life and its ability to thrive in diverse environments across the universe. In astrobiology, these discoveries are foundational, helping to shape our understanding of life's resilience. The implications of these findings extend far beyond Mars, sparking interest in other celestial bodies as potential habitats for life. Scientists are now more determined than ever to explore not only Mars, but also moons and planets that were once considered inhospitable. The presence of microbial fossils on Mars offers a glimpse into the possibility that life may not be unique to Earth. It calls us to look beyond our own planet and explore the wider universe for signs of life, whether microbial or more complex. In our ongoing search for life beyond Earth, researchers have developed cutting-edge technologies to detect biosignatures on distant planets. Space telescopes, equipped with specialized instruments, are now capable of analyzing the atmospheres of exoplanets to detect the presence of gases such as oxygen and methane. When found together in significant quantities, these gases may indicate the presence of biological activity. Spectroscopy, a key tool in this process, involves breaking down light emitted or absorbed by a planet's atmosphere into its constituent wavelengths. By studying these wavelengths, scientists can identify the chemical signatures of molecules, offering valuable clues about a planet's potential to support life. For example, the presence of chlorophyll, a molecule used by plants on Earth, can suggest that photosynthetic life exists elsewhere in the universe. This method, combined with transit photometry, which measures the slight dimming of a star's light when a planet passes in front of it, has already led to the discovery of Earth-sized planets in the habitable zones of their stars. These planets, with conditions similar to those on Earth, are now prime candidates for further study. Together, these advanced techniques are providing us with the tools to probe distant worlds for signs of life in ways we could only dream of just a few decades ago. As our knowledge of these far-off planets deepens, so too does our understanding of the complex conditions necessary for life to flourish. The search for life beyond Earth is one of the most profound scientific quests of our time. Each discovery, whether it is the detection of a distant exoplanet or the identification of a microbial fossil on Mars, drives us closer to answering one of humanity's oldest and most enduring questions. Are we alone in the universe? As we continue to look toward the stars, the mysteries of the cosmos unfold, inviting us to imagine a future where humanity might not just be observers of the universe, but active participants in its greater story. The journey is far from over, but with each new breakthrough, we are moving closer to uncovering the truth. The realm of cosmic exploration has taken monumental strides in recent years, fundamentally reshaping our understanding of the universe and life itself. Advances in computer modeling and artificial intelligence have proven to be invaluable tools, enabling researchers to process vast amounts of data gleaned from astronomical observations. This powerful data analysis allows scientists to sift through the noise, distinguishing between potential biosignatures, indicators of life, and false positives that might arise from non-biological processes. With every breakthrough, the once distant dream of answering the age-old question, "Are we alone in the universe?" becomes a little more tangible. It sparks a sense of wonder, propelling humanity to seek answers to the mysteries that still elude us. One fascinating area of research that has emerged from this exploration is the study of cosmic radiation exposure. Cosmic radiation, which consists of high-energy particles constantly bombarding our planet from outer space, has opened exciting new avenues for understanding the origins and evolution of early life on Earth. This radiation penetrates the atmosphere, reaching the surface of the planet, and it potentially has profound effects on living organisms. As scientists delve deeper into its effects, they uncover important insights into how early life might have adapted to these environmental challenges. One of the most captivating aspects of this research lies in the role of cosmic radiation in the formation of organic molecules. When high-energy particles collide with atmospheric elements, they can trigger a cascade of chemical reactions that result in the production of a wide range of organic compounds. These compounds, in turn, are the essential building blocks of life. This suggests that cosmic radiation could have played a significant role in the creation of the primordial soup, the conditions from which life emerged billions of years ago. In this way, the environment of space may have shaped the biochemical origins of life on Earth, offering a deeper understanding of the factors that made life possible. Moreover, investigations into radiation exposure have led to fascinating discoveries regarding how early life forms may have developed mechanisms to resist such harsh conditions. Some microorganisms today exhibit remarkable resilience to high levels of radiation, and these resilient organisms could hold key clues to understanding how life on Earth adapted to an environment that was radically different from the one we experience today. The radiation levels on early Earth were likely much higher, presenting a significant challenge to the survival of life. Studying how these early organisms survived in such an environment is like piecing together a historical puzzle, helping scientists trace the evolution of life and its remarkable ability to adapt. The implications of these findings extend far beyond Earth. If cosmic radiation was indeed a crucial factor in the evolution of life here, Similar processes could be at play on other planets or moons that have atmospheres exposed to space. This new perspective encourages astrobiologists to reconsider the conditions required for life to thrive elsewhere in the cosmos. The idea that our cosmic environment plays a significant role in shaping life's origins opens up exciting possibilities about the interconnectedness of life throughout the universe. It reinforces the notion that life may not be as isolated as we once thought, prompting us to expand our search for life to places previously considered inhospitable. As research continues, the narrative surrounding cosmic radiation and life's beginnings only becomes more compelling, unveiling a more complex and interconnected story than we could have imagined. Traditionally, we have viewed galaxies as isolated islands floating in the vast sea of space, each spinning independently in its own corner of the cosmos. However, recent astronomical observations have revealed a far more dynamic and interconnected picture. Galaxies, it turns out, are not solitary entities. They are often closely connected, actively interacting in dramatic ways. These interactions, once thought to be rare, are now understood to be a more common phenomenon than previously imagined. One of the most striking examples of these interactions can be seen in galaxy pairs or groups. When two galaxies come into close proximity, their gravitational forces can lead to extraordinary distortions in their shapes. Sometimes these galaxies begin to merge, forming a larger new galaxy altogether. In other cases, one galaxy may strip material from another, triggering the formation of new stars in the process. These types of galactic interactions challenge the long-held belief that galaxies evolve in isolation. Instead, they suggest that the cosmos is teeming with relationships, constantly in motion, where galaxies are far from solitary. They are participants in an ongoing cosmic dance. Adding another layer of complexity to our understanding of the universe, astronomers have also uncovered the existence of colossal galaxy filaments. These monumental structures form part of the vast cosmic web, a network of interconnected galaxies stretching across the universe like threads in a grand tapestry. Through this cosmic web, material and energy flow across unimaginable distances, facilitating interactions between galaxies that may seem separated by vast expanses of space. This new understanding is reshaping the way we think about cosmic structures, offering fresh insights into phenomena like dark matter and the large-scale distribution of galaxies. What's most remarkable about these discoveries is the way they challenge our previous assumptions about the universe. Instead of seeing galaxies as isolated, independent entities floating alone in space, we now recognize that they are part of a grand, interconnected system. This realization not only enriches our understanding of how galaxies form and evolve, but also stirs a sense of wonder about the intricate fabric of the cosmos. It reminds us that even in the immense vastness of space, no part of the universe exists in complete isolation. Another groundbreaking development that has captured the attention of scientists in recent years is the evolving understanding of dark matter. For a long time, dark matter was viewed as an enigmatic substance that barely interacts with ordinary matter except through gravity. However, new observations are suggesting that the relationship between dark matter and ordinary matter might be more complex than we had previously imagined. These findings are reshaping our understanding of how the universe itself came to be. One of the most significant developments in dark matter research is the growing body of evidence suggesting that dark matter particles might be capable of interacting with each other or with normal matter in ways that go beyond gravitational attraction. These interactions could have profound implications for the formation and evolution of galaxies and galaxy clusters. For instance, if dark matter particles clump together more efficiently than we thought, it could lead to faster galaxy formation, altering the way we model the growth of cosmic structures. This new understanding of dark matter has the potential to revolutionize our cosmological models, requiring us to rethink the dynamics between dark and visible matter in the universe. As research continues, it is likely that these interactions will play a key role in shaping our understanding of how galaxies and other cosmic structures evolve. The more we learn about dark matter, the clearer it becomes that the universe is far more complex and interconnected than we could have ever imagined, making the journey of discovery all the more exhilarating. The way we think about dark matter and its distribution within galaxies has undergone a significant transformation. Traditionally, scientists assumed a smooth and uniform spread of dark matter throughout galaxies. This belief held sway for decades, forming the cornerstone of many models. However, recent advancements, driven by both cutting-edge simulations and ever more precise observational data, have shattered this conventional view. The universe's unseen substance may not be as evenly distributed as once thought. Instead, dark matter could be creating far more intricate structures, reshaping our understanding of galactic formation. This revelation has prompted a rigorous reevaluation of theoretical models. The new data suggests that dark matter's role in shaping galaxies is more complex than previously imagined, and scientists have scrambled to refine their predictions. These refinements now take into account emerging observations, such as the clustering of galaxies and the unique features of the cosmic microwave background radiation. As our models grow more sophisticated, they challenge and refine the very foundation of our cosmic theories, pushing the boundaries of what we know. Each new discovery serves as a stepping stone toward a more complete understanding of the universe, one that encompasses not just the visible matter we observe, but the vast, invisible forces that govern its structure. These efforts continue to probe the depths of dark matter, with the goal of uncovering its secrets. In doing so, we inch closer to a unified model that explains not only the visible universe, but also the complex, unseen forces that are just as integral to its evolution. These studies hold the promise of deepening our understanding of cosmic evolution and refining our understanding of our place in the universe. In parallel, the relationship between the solar cycle and Earth's climate has been a subject of fascination for scientists for many years. The solar cycle, which spans approximately 11 years, is marked by fluctuations in solar activity, such as changes in sunspots, solar flares, and shifts in the sun's magnetic field. These variations in solar behavior are known to have a subtle yet measurable impact on Earth's climate. Increased solar activity tends to correlate with a slight rise in global temperatures, as a more active sun emits more radiation. This surge in energy can influence weather patterns and atmospheric conditions, albeit in a relatively modest manner. Recent research, leveraging sophisticated satellite data, has uncovered a clear link between heightened solar activity and warmer global temperatures. However, scientists are quick to point out that while the sun's role is significant, it is not the dominant factor in the current warming trend. The far more profound influence comes from human activities, particularly the emission of greenhouse gases. A groundbreaking study published in recent years has gone further to explore the interaction between solar radiation and Earth's atmosphere. Researchers found that during the solar maximum, when sunspots peak, there is an uptick in the energy reaching Earth's surface. However, this effect is still relatively small when compared to the far more dramatic changes brought about by human-induced climate change. Ultimately, while solar cycles do contribute to Earth's climate variations, they operate within a much larger framework of factors. These include volcanic eruptions, ocean currents, and human actions. The current scientific consensus acknowledges the sun's influence, but recognizes that the rapid pace of climate change today is primarily driven by human activities. This understanding highlights the urgent need for continued exploration of our solar system, while also remaining vigilant about the health of our planet. The lessons learned from studying the solar cycle will undoubtedly deepen our appreciation for the delicate balance that sustains life on Earth. Star formation occurs in a variety of environments across the universe, each contributing uniquely to the ongoing process of galactic evolution. In the dense cores of galaxies, stars tend to form in large, tightly bound clusters, and this process occurs rapidly. These stellar nurseries give rise to massive stars that burn intensely but briefly, ultimately ending their lives in dramatic supernovae. These explosive events not only enrich the surrounding medium with heavier elements, but also play a pivotal role in influencing the formation of other stars and planetary systems. These interactions offer valuable insights into the broader life cycle of galaxies. In contrast, in more diffuse regions of a galaxy, star formation takes place at a much slower pace. These areas produce stars over millions, sometimes even billions of years. The stars that emerge in these less active regions are typically smaller and less luminous. By studying these diverse stellar populations, astronomers have learned much about how varying environmental conditions affect the rate and nature of star formation. This, in turn, has provided essential knowledge about the long-term development and structure of galaxies. One of the most fascinating aspects of star formation is how galaxy interactions can trigger new waves of star birth. When two galaxies collide, their gravitational forces can compress gas and dust, setting off a cascade of new star formation. This process, known as a starburst, often leads to the creation of a new generation of stars that would not have formed in isolation. These interactions underscore the role of environmental factors and galactic mergers in shaping the evolutionary paths of galaxies, influencing everything from the stars within them to the very structure of the galaxies themselves. As observational technology continues to advance, scientists are gaining an even deeper understanding of the conditions that foster star formation. New findings challenge previous assumptions about galaxy growth and highlight the intricate relationships between different regions of space. These revelations push the boundaries of our knowledge, demonstrating that the evolution of galaxies is an ongoing and ever-changing process. Each new discovery rewrites part of the universe's story, taking us closer to a more complete and nuanced understanding of cosmic history. The evolution of telescope technology is another story of profound transformation, one that has dramatically shifted our understanding of the cosmos. In the early days of astronomy, the tools available were rudimentary, consisting of simple refracting telescopes that allowed astronomers to glimpse the wonders of the night sky. However, these early instruments were limited in their capacity to collect light, meaning that many distant celestial objects remained beyond our reach. As technology advanced, so did our ability to explore the universe. Larger, more powerful telescopes began to emerge, capable of capturing fainter light from more distant objects. One of the most significant innovations came with the advent of reflecting telescopes, which use mirrors instead of lenses. This innovation allowed for the construction of larger instruments capable of gathering more light without the distortion caused by glass lenses. One of the most iconic examples of this is the Hubble Space Telescope, launched in 1990. Orbiting far beyond Earth's atmosphere, Hubble provides images free from the distortions caused by atmospheric interference. Hubble's stunning images have opened our eyes to the grandeur of distant galaxies, nebulae, and countless other cosmic phenomena, reshaping our perception of the universe. The breathtaking clarity and detail provided by these observations have allowed astronomers to peer deeper into the cosmos than ever before, offering unparalleled views of the universe's farthest reaches. This leap forward in observational capability has brought us closer to understanding the universe's vast and intricate nature, forever altering our cosmic perspective. The leap in technology, specifically the development of radio and infrared telescopes, has unlocked entirely new avenues for exploring the cosmos. These advanced telescopes can detect wavelengths of light that are invisible to the naked eye, offering us unprecedented insights into the early universe. For the first time, scientists have the tools to study cool, dim celestial bodies such as brown dwarfs and distant exoplanets that would otherwise remain hidden in the vast reaches of space. Ground-based instruments like the Very Large Array, VLA, and space observatories like the James Webb Space Telescope, JWST, have expanded our reach even further, enabling groundbreaking discoveries about the formation of stars, the chemical composition of exoplanetary atmospheres, and the early stages of cosmic evolution. With each new telescope that becomes operational, our understanding of the universe deepens, and the secrets of the cosmos continue to unfold. The ability to peer deeper into space does more than just expand our knowledge, it fuels our collective imagination. Every stunning discovery reminds us of just how much remains to be explored. These technological advancements in telescope design are vital to unlocking the mysteries that lie beyond our reach. In essence, they serve as the stepping stones for future generations to better understand our place in this vast, ever-expanding universe. While telescopes allow us to view distant celestial phenomena from afar, space probes offer an entirely different level of exploration. These robotic explorers serve as our eyes and ears beyond the boundaries of Earth, enabling us to examine distant planetary systems, moons, and comets up close. Unlike telescopes, which gather light and other forms of radiation from great distances, space probes physically travel to the locations of interest. By venturing closer to celestial bodies, they gather first-hand data and send it back to Earth for analysis. Each space probe mission is designed with specific scientific goals in mind. Some probes study the atmosphere and surface conditions of other planets, while others focus on the composition of asteroid belts or investigate the magnetic fields of distant worlds. Equipped with an array of sophisticated instruments, these probes can measure temperature, radiation levels, geological features, and even search for signs of life, furthering our understanding of the universe and the potential for life beyond our planet. One of the most remarkable aspects of space probes is their ability to operate in extreme environments where humans cannot survive. For example, the Voyager spacecraft, launched in the 1970s, are still transmitting valuable data about the far reaches of interstellar space more than 4 decades later. Likewise, the Mars rovers have provided us with a detailed look at our neighboring planet, revealing a complex history of water and geological activity that may one day pave the way for human exploration. These missions represent much more than a quest for knowledge. They embody our resilience and our unyielding curiosity. Each probe and mission serves as a testament to our desire to understand the fundamental questions about the universe. How do planetary systems form? Is there life beyond Earth? With each mission, we connect more deeply to the cosmos, slowly unraveling its mysteries, one probe at a time. The integration of artificial intelligence, AI, into astrophysical research has revolutionized the way scientists approach data analysis. Traditionally, astronomers face the daunting task of sorting through massive data sets, gathering information from telescopes and satellites. The universe presents an unfathomable amount of data, from faint signals emitted by distant stars to the intricate patterns of galaxies, and human analysts were often overwhelmed by the sheer scale of it all. Enter AI, an indispensable tool capable of recognizing complex patterns, sorting through vast amounts of data, and drawing conclusions at speeds no human could match. One of the most notable contributions of AI has been its ability to identify celestial phenomena that might otherwise go unnoticed. For instance, machine learning algorithms are now employed to detect exoplanets. By analyzing the slight dimming of stars as a planet passes in front of them, AI systems can detect minute variations in brightness, even amidst the noise of the surrounding data. This capability has led to the discovery of thousands of exoplanets, expanding our understanding of the potential for life beyond our solar system. AI is also transforming the way we detect gravitational waves, ripples in space-time caused by massive cosmic events, such as black hole collisions. The immense volume of data generated by detectors like LIGO can overwhelm traditional methods of analysis, but AI's ability to process and identify potential gravitational wave events has greatly increased the speed and accuracy of this research. With AI's help, astronomers can quickly identify and investigate these phenomena, coordinating with observatories to observe them across multiple wavelengths. As AI continues to evolve, its role in astrophysics will only grow. Sophisticated algorithms and machine learning models will pave the way for even more profound discoveries, opening up new frontiers in the exploration of the universe. The partnership between human curiosity and machine precision will push the boundaries of our understanding, making the stars more accessible than ever before. The outer planets of our solar system, long considered enigmatic and distant, have become of intense exploration in recent years. Missions like NASA's Juno spacecraft and the European Space Agency's Jupiter Icy Moons Explorer, JUICE, have provided us with an invaluable wealth of information about these massive, mysterious planets. Juno, in particular, has revealed that Jupiter, the largest planet in our solar system, boasts an intricate and chaotic magnetic field, much more powerful and complex than we previously understood. This new knowledge helps us better appreciate Jupiter's dynamic environment and its crucial role in the solar system's overall structure. Perhaps one of the most fascinating revelations from these missions has been the study of weather systems on gas giants. Juno has captured breathtaking images of Jupiter's swirling storms, including the iconic Great Red Spot, a storm that has been raging for centuries. Data from the spacecraft suggests that these storms extend deep into the planet's atmosphere, far below the cloud tops, raising new questions about the thermal dynamics of gas giants and how such immense storms can maintain their energy over extended periods. As we continue to explore the outer planets and their moons, we uncover new layers of understanding about the solar system and the forces that shape it. Each mission contributes to a growing body of knowledge and bringing us closer to understanding the origins of these massive worlds and their role in the broader cosmic story. With each new discovery, we inch closer to answering the fundamental questions about the nature of our solar system and, by extension, the universe itself. Our explorations of the cosmos are far-reaching, and yet they are not confined to the familiar boundaries of Jupiter. Take, for example, Saturn's moon Enceladus. Through missions like Cassini, we've uncovered astonishing secrets about this distant world. Beneath its icy crust lies a vast subsurface ocean, a discovery that could redefine our understanding of the conditions required for life. Geysers erupting from Enceladus's south pole, spewing water vapor and organic materials into space, offer compelling evidence of hydrothermal activity occurring on its seafloor. This revelation has placed Enceladus at the forefront of astrobiological research, sparking debates on its potential to harbor life, particularly microorganisms. As we continue to explore the mysteries of Enceladus, we are not just deepening our understanding of one particular moon. These findings, along with similar breakthroughs across the solar system, are advancing our broader comprehension of planetary formation and evolution. This knowledge extends well beyond our own solar system, impacting our view of the entire universe. With each discovery, we peel back layers of complexity, revealing not just the unique characteristics of distant worlds, but also gaining a greater appreciation for the intricate workings of our own cosmic neighborhood. This ongoing research fuels curiosity, driving new missions and inspiring future generations of explorers who will carry the torch forward. In recent years, advancements in imaging technologies have revolutionized the way we explore space, making what once seemed like science fiction a present-day reality. One of the most transformative innovations has been the advent of high-resolution telescopes equipped with adaptive optics. This technology allows astronomers to correct the distortions caused by Earth's atmosphere, producing images that reveal intricate details of celestial objects once hidden from view. These telescopes, like the very ones that first brought us images of the distant planets, are providing us with a more detailed and accurate understanding of the universe. Further amplifying our cosmic vision are space-based observatories like the Hubble Space Telescope and the James Webb Space Telescope. These instruments operate beyond Earth's atmosphere, free from the distortions of air and weather, providing us with pristine images of distant stars and galaxies. The James Webb Space Telescope, in particular, offers unparalleled capabilities in infrared astronomy. This allows scientists to peer through the dust clouds that often obscure the birthplaces of stars and planetary systems. By detecting infrared light, Webb provides a glimpse into the early formation of stars and allows us to observe galaxies as they existed billions of years ago, long before the Earth was even born. In addition to these optical and infrared advancements, the realm of radio astronomy has opened new frontiers in our understanding of the universe. Radio telescopes, including the Event Horizon Telescope, allow us to observe phenomena that are invisible in visible light. The Event Horizon Telescope's groundbreaking achievement, the first ever image of a black hole's shadow, was a monumental moment in scientific history. This achievement revealed the mysterious regions surrounding black holes and gave us an unprecedented glimpse into their complex behavior. Such discoveries are crucial in understanding the forces of gravity, matter, and energy at the very edges of these cosmic giants. Yet, the tools we use to observe the universe are not the only factors driving our progress. Advances in computer algorithms and machine learning are proving essential in helping scientists analyze the immense volumes of data we now collect from space. These technologies are able to sift through this data, identifying patterns and anomalies that may otherwise be missed by the human eye. Through this process, we are beginning to uncover secrets of the universe that were once hidden in plain sight. With each new revelation, we are forced to confront even greater mysteries, provoking deeper questions about the nature of existence and our place in the cosmos. One of the most profound challenges in astrophysics is understanding the nature of time. Time is not a simple linear progression as it is often perceived in our daily lives. Instead, it is intricately woven into the very fabric of space, creating a dimension that is both elusive and complex. The concept of time's relativity, first introduced by Albert Einstein over a century ago, is central to our understanding of the universe. According to Einstein's theories, time does not move uniformly for all observers. It stretches and compresses depending on the gravitational fields present and the relative speeds of different observers. This revelation makes it difficult to establish a definitive understanding of time, as it varies from place to place and from one observer to another. Another significant obstacle lies in the measurement of time across the vast distances of the cosmos. Events in the universe unfold on scales that are often too enormous for us to fully grasp. For instance, when we observe a star's violent explosion in a supernova, we are seeing light that has traveled millions of years to reach us. As such, accurately measuring the timing of these events is no simple task. Although light can serve as a cosmic clock, the behavior of light is not always predictable. Its interaction with cosmic materials introduces additional uncertainties that make precise measurement difficult. Moreover, when we observe celestial bodies in motion, we are confronted with the phenomenon of time dilation. For example, an astronaut traveling close to the speed of light would experience time at a different rate than someone on Earth. This discrepancy highlights the relativity of time and presents further challenges to establishing a universal timeline for the entire cosmos. As we attempt to understand the intricacies of time, we are continually reminded that it is a concept that resists simple explanation, leaving us to wonder whether we will ever fully grasp its true nature. Finally, the very essence of time remains one of the most perplexing and unresolved questions in the realm of scientific inquiry. For centuries, the nature of time has captivated the minds of researchers, philosophers, and cosmologists alike. While time is something we all experience daily, its true nature is still elusive. Is it a fundamental component of the universe like space and matter? Or is it an emergent property arising from the interaction of deeper, more fundamental phenomena? This question, which cuts to the heart of the laws governing our universe, continues to fuel debates in astrophysical research and beyond. As our knowledge of the cosmos deepens, so too will our understanding of time, transforming it from a simple unit of measurement into something much more profound, a key to unraveling the vast history of existence itself. One of the most exciting breakthroughs in our understanding of time and matter has come from groundbreaking experiments conducted right here on Earth. These experiments have unprecedented insights into how matter behaves under extreme conditions, conditions that are found only in the most hostile corners of the cosmos. By recreating these environments in laboratories, scientists are able to observe how particles, forces, and materials behave when subjected to cosmic extremes. One of the most prominent tools in this quest is the Large Hadron Collider, LHC, the world's most powerful particle accelerator. In this state-of-the-art facility, particles are accelerated to speeds near the speed of light and then collided, mimicking the conditions that existed just moments after the Big Bang. These collisions provide scientists with a wealth of information, shedding light on the fundamental building blocks of the universe and the forces that govern them. But the exploration doesn't end there. In laboratories on Earth, researchers have also replicated the extreme temperatures and pressures found deep inside stars or during the catastrophic explosions of supernovae. For instance, scientists have developed methods to compress tiny samples of matter using incredibly powerful lasers. This process simulates the immense energy conditions that prevail in the cores of stars, providing insights into nuclear fusion, the very process that powers stars and creates the elements that make up everything around us. Without this knowledge, we would lack an understanding of how the very building blocks of matter are formed. Beyond the study of nuclear processes, scientists are also turning their attention to the mysteries surrounding neutron stars. Celestial objects so dense that a single cubic centimeter of their material weighs as much as a mountain on Earth. The magnetic fields around stars are unimaginably strong, far stronger than anything we can generate in laboratories on Earth. Nevertheless, by experimenting with high magnetic fields and ultra-low temperatures in lab settings, researchers are uncovering the secrets of matter under such extreme conditions. This work is providing critical insights into the enigmatic cores of neutron stars and their potential role in the larger structure of the universe. Moreover, the study of cosmic rays, high-energy particles originating from deep space, has allowed scientists to investigate how matter reacts when bombarded with energy levels far beyond anything experienced on Earth. These ultra-energetic particles carry vital information about the fundamental laws of physics, offering a unique perspective on the universe's workings that cannot be replicated by any other means. All of these experimental endeavors, ranging from particle accelerators to laser-driven simulations and the study of cosmic radiation, are shedding new light on the most fundamental aspects of matter and the universe itself. They're not just probing the intricate details of physics, they're allowing us to see the universe as it truly is, an immensely complex, ever-evolving entity full of mysteries waiting to be unlocked. One of the most fascinating and perplexing concepts in modern physics is time asymmetry. This idea refers to the observation that time seems to flow in one direction, from the past to the future. While we can recall memories, witness events unfolding in real time, and experience the passage of time, we cannot reverse it. The past is behind us, and the future lies ahead, unreachable and unknown. This observation leads to some profound questions about the very structure of the universe. Why does time flow forward? What does this imply about the nature of the universe itself? A key clue to understanding time's irreversible nature lies in the second law of thermodynamics. This law states that in an isolated system, the level of disorder, or entropy, tends to increase over time. Picture a glass of ice water. As time passes, the ice melts and the water becomes uniformly mixed. The system moves toward a state of greater disorder, or equilibrium. This trend toward greater entropy is a crucial indicator that time has a preferred direction. It is this increase in entropy that hints at the universe's origins, suggesting that it began in a state of extremely low entropy, perhaps at the moment of the Big Bang. The second law of thermodynamics invites further questions. If the universe started in such an orderly state, what does this tell us about its future? As the universe expands and evolves, it continually moves toward higher entropy, chaos, disorder, and dispersion of energy. Over time, the structure of the universe has become more complex, with matter clumping together to form galaxies, stars, and planets. These processes, driven by the interplay of time and entropy, offer a clue about the ultimate fate of the universe. Will it continue expanding forever, growing increasingly cold and empty, as some theories suggest? Or is there a possibility of cyclical rebirth, where the universe undergoes periodic phases of expansion and contraction? As scientists probe deeper into these questions, it becomes increasingly clear that time is far from a simple linear progression. Time's asymmetry may indicate that the fabric of the universe is far more intricate than we can currently comprehend. This linear flow of time, the so-called arrow of time, is entwined with fundamental questions about causality, the possibility of time travel, and the eventual evolution of the cosmos. As researchers dive into these mysteries, they find themselves navigating a space where the boundaries between physics and philosophy blur, where the very essence of existence is up for exploration and wonder. At the heart of these investigations lies the theory of cosmic inflation, a radical idea that proposes the universe underwent a rapid, exponential expansion in the first moments following the Big Bang. This theory not only provides an explanation for the uniformity of the cosmos, but also offers insights into its ultimate fate. One of the most profound implications of inflation is its connection to the ongoing expansion of the universe. Observations have shown that the universe is not only expanding, but doing so at an accelerating rate. This discovery led to the introduction of the mysterious concept of dark energy, a force that seems to be pushing galaxies apart. According to inflationary theory, the universe's expansion could continue indefinitely, stretching into the farthest reaches of space. In this scenario, galaxies would drift further and further apart, eventually becoming isolated in an increasingly cold and dark cosmos. However, not all variations of inflationary theory predict such a bleak future. Some propose the idea of a cyclical universe, one in which the cosmos undergoes repeated cycles of expansion and contraction. Each cycle could be followed by a rebirth, resetting conditions to a fresh, orderly state. This cyclical model suggests a universe that is not only dynamic, but potentially eternal, with an endless series of renewals. As research into cosmic inflation continues, scientists are refining their understanding of the universe's ultimate fate. With each new discovery, they are unveiling new possibilities, from the possibility of infinite expansion to the intriguing prospect of periodic rebirths. These ideas offer us a window into the future of the universe, while also providing clues about its distant past. As we continue to unravel the mysteries of inflation and its implications, we are drawn closer to understanding the vast, ever-changing cosmos that surrounds us and our place within it. In a similar vein, the study of black holes has sparked a dramatic shift in how we understand time, space, and the very nature of reality. Traditionally, time and space were viewed as immutable backdrops against which the events of the universe unfolded. But black hole thermodynamics, an emerging field of research, has challenged this view, revealing that the very fabric of space-time can be altered by the immense gravitational forces exerted by these enigmatic objects. As scientists delve deeper into the complex behavior of black holes, they continue to discover unexpected phenomena that could reshape our understanding of time, space, and the universe as a whole. The exploration of time, space, and the cosmos is far from over. Each experiment, each observation brings us closer to understanding the profound mysteries that lie at the heart of existence. And as our knowledge evolves, so too will our grasp of the universe, an ever-unfolding story that has yet to reveal all of its secrets. However, the profound properties of black holes introduce a complex and ever-evolving relationship between dimensions, fundamentally altering how we perceive the very fabric of reality. Black holes, once viewed solely as cosmic drains capable of devouring everything in their vicinity, have now emerged as pivotal players in our quest to uncover the universe's most profound mysteries. Among the most captivating aspects of black hole thermodynamics is the relationship between entropy and information. It was proposed that black holes have entropy, which represents a measure of disorder or missing information. This discovery implies that the information about everything that falls into a black hole is not truly lost. Instead, it is encoded on the surface, on what we call the event horizon. This breakthrough led scientists to reconsider the nature of reality itself, suggesting that the universe we experience in 3 dimensions might be an emergent phenomenon, a product of a deeper, more complex 2-dimensional realm of data that exists beyond our perception. Furthermore, the concept of space-time has evolved dramatically, particularly in the context of black holes. Space and time are no longer rigid structures, but rather fluid and malleable entities, reshaped by the immense gravitational forces at the heart of black holes. The event horizon acts as a boundary, beyond which nothing can escape, not even light, hinting that reality itself behaves in ways that defy conventional understanding under such extreme conditions. This perspective encourages scientists to theorize that space-time, at its most fundamental level, could be woven from the same informational fabric that defines black hole information. These revolutionary models of time and space challenge our classical intuitions and prompt deep philosophical questions about the very nature of the universe. Can we truly know the limits of reality? If information can persist even in the deepest, most inaccessible parts of a black hole, what does that suggest about the nature of existence itself? As research continues to progress, we stand at the precipice of redefining our understanding of the cosmos. Black holes are no longer mere cosmic enigmas. They have become keys to unlocking the ultimate nature of reality. Beyond the awe-inspiring phenomena of black holes, another often overlooked yet vital component in our understanding of the universe is cosmic dust. These tiny, seemingly insignificant particles, composed primarily of carbon, silicon, and metals, play an essential role in the formation of galaxies, stars, and even planets. Cosmic dust is not merely an annoyance for astronomers. It is, in fact, an invaluable clue to the processes that shape the cosmos. Recent discoveries have revealed that cosmic dust forms in the violent aftermath of events like supernovae, where massive stars, having exhausted their nuclear fuel, explode in a spectacular burst. This star dust, scattered across the cosmos, is far more than just debris. It holds crucial information about the elemental makeup of the universe and how these elements come together to create new celestial bodies. For instance, studies of cosmic dust have demonstrated its role as a catalyst for the formation of complex molecules, which are integral to the chemistry of life as we know it. Moreover, cosmic dust has been observed in some of the most distant and ancient galaxies, offering astronomers a glimpse into the early universe. By analyzing dust at these vast distances, scientists can reconstruct the timeline of star formation and galaxy evolution. It turns out that dust not only shelters and nurtures young stars, but also influences their growth and development, making it an indispensable part of the ongoing life cycle of galaxies. It acts as a bridge between the old and the new, linking the ancient past of the universe to its dynamic present. The study of cosmic dust extends beyond the birth and evolution of stars. It has far-reaching implications for understanding the formation of planetary systems. As dust particles collide and stick together, they form larger objects, such as asteroids and comets. In this way, cosmic dust is not simply a byproduct of stellar processes. It is an active participant in the ongoing creation of the universe. The continuous exploration of cosmic dust reminds us that even the smallest particles can have profound lasting effects on the cosmos. The International Space Station, ISS, a remarkable feat of human engineering and scientific ambition, has served as a cutting-edge laboratory for studying the effects of prolonged space travel on both human bodies and technology. Since its launch, astronauts have lived and worked aboard the ISS for extended periods, providing invaluable insights into how our bodies react to the unique conditions of microgravity and exposure to cosmic radiation. These observations have been crucial in understanding the physical changes that occur in space, such as muscle atrophy, bone density loss, and changes in vision. One key lesson learned from the ISS is the importance of maintaining physical fitness during long-duration missions. Astronauts aboard the station must exercise daily to combat the effects of muscle and bone deterioration. This realization has led to the development of exercise regimens specifically designed to be used on long-duration space missions, such as a potential journey to Mars, which may last several years. The necessity for physical activity, coupled with a balanced diet, underscores the fact that human health must remain a central focus in planning for future deep space missions. Psychological well-being is another crucial factor, especially given the isolated and confined environment aboard the ISS. Astronauts live and work in close quarters for extended periods, and the strain of this confinement can take an emotional toll. Research into the dynamics of crew interactions and coping strategies is ongoing, with scientists working to develop effective communication and support systems for astronauts. As we look ahead to future missions to distant destinations like Mars, these lessons will be essential in ensuring that astronauts not only survive, but thrive in the challenging conditions of space. As humanity continues to push the boundaries of space exploration, the experiences aboard the ISS offer us a vital window into the challenges we must overcome to make long-duration space travel a reality. Through a combination of physical fitness, mental resilience, and cutting-edge technology, we are laying the groundwork for a future where deep space exploration becomes a part of humanity's journey. The ISS has become not only a laboratory for scientific discovery, but also a proving ground for the challenges and triumphs of exploring the unknown reaches of space. The International Space Station, ISS, has become a critical testbed for human space exploration, driving innovations that directly impact the future of long-duration missions. Among the most vital technologies developed aboard the ISS are life support systems such as water recycling and air purification. These technologies are more than just advancements. They are necessities for sustaining life on missions far from Earth, where resupplying from our planet becomes impractical. As a result, the ISS is not just a platform for scientific research and space exploration, It is a cornerstone in humanity's quest to make long-term space travel viable. The lessons learned on the ISS will undoubtedly play a pivotal role in shaping the future of interplanetary exploration. In this context, the ISS provides valuable insights not only about life support, but also about the broader implications of space travel. With its sophisticated experiments and onboard systems, the ISS simulates conditions that will be encountered on extended missions to distant planets like Mars. This research has already begun to influence future space missions, from resource utilization to human health in space. The progress made on the ISS is paving the way for humanity's future as an interplanetary species, allowing us to understand the challenges of living on other worlds. In tandem with life support systems, recent research from the ISS has also enhanced our understanding of solar wind and its impact on Earth. The solar wind, a stream of charged particles emitted by the sun, plays a fundamental role in shaping space weather, influencing not only our planet's atmosphere, but also its technology and climate systems. As these particles interact with Earth's magnetic field, they can create stunning auroras, the natural light displays near the poles. However, these cosmic events are not just beautiful, they carry risks as well. Solar storms can disrupt satellite communications, interfere with GPS systems, and even cause power grid failures on Earth. Beyond these immediate threats, scientists are now investigating how the solar wind may influence Earth's climate over extended periods. Although the relationship remains complex, early findings suggest that variations in solar activity might influence cloud formation via cosmic rays, which are influenced by the solar wind. These variations could potentially impact regional weather patterns and even contribute to long-term climate changes. Understanding these intricate interactions is crucial, not only to protect our technological infrastructure, but also to inform how we might adapt to future climate shifts. The study of solar wind and space weather also holds promise for future space exploration. As humanity ventures further into the cosmos, understanding the effects of solar radiation on spacecraft and astronauts will be vital. With this knowledge, we can better protect space missions and ensure the safety of astronauts traveling to destinations like Mars or beyond. The ISS, in its role as a testbed for space travel, offers the perfect environment for these groundbreaking studies. Human space exploration has also deepened our understanding of life beyond Earth. By studying other celestial bodies, we are learning about the conditions necessary for habitability. Missions to planets and moons, such as Mars and the icy satellites of Jupiter and Saturn, are revealing critical information about their atmospheres, surfaces, and potential resources. Through this research, we are discovering which places in the universe might support life, even if it differs vastly from the life we know on Earth. One of the most striking discoveries in this context is the existence of extremophiles, organisms on Earth that thrive in extreme environments once thought inhospitable. These resilient life forms have been found in the most inhospitable conditions, such as boiling hot springs and frozen Antarctic lakes. The discovery of extremophiles suggests that life could exist in similar extreme environments elsewhere in the universe. For instance, the icy moons of Jupiter and Saturn, with their subsurface oceans, may harbor life forms adapted to conditions vastly different from those on Earth. Furthermore, human missions to space, such as the ongoing research aboard the ISS, enable scientists to conduct experiments in microgravity. In this unique environment, biological processes behave in ways that are not possible under Earth's gravity. These studies help us understand how life might function in space and offer insights into the origins of life itself. By observing how organisms adapt to space conditions, researchers are unlocking clues about the potential for life to evolve and develop on other planets. With each new mission, whether manned or robotic, our understanding of life's possibilities expands. These missions contribute to the growing body of knowledge about whether life exists elsewhere in the universe, fueling our curiosity and ambition to explore beyond the confines of Earth. As technology advances, so too does our ability to search for signs of life on distant worlds, whether through telescopes, landers, or advanced rovers. In addition to exploring life beyond Earth, one of the most exciting frontiers of space research involves cosmic rays. These high-energy particles from outer space have long intrigued scientists, particularly because of their impact on biological organisms. When cosmic rays collide with atoms in Earth's atmosphere, they produce secondary radiation and free radicals, which can have profound effects on living organisms. Some researchers believe that cosmic rays may have played a pivotal role in the evolution of life on Earth, as they induce genetic mutations that contribute to the genetic diversity essential for evolution. These cosmic rays might not only affect life on Earth, but could also provide critical information about the origins and evolution of life. By studying their effects, we are uncovering a surprising truth. These seemingly destructive forces could have shaped the very building blocks of life. On Earth, nearly 1 million cosmic ray events interact with living cells each year, suggesting that cosmic rays could have played a role in guiding the complexity of life as we know it. As we continue to explore the cosmos, we are not just discovering new planets and moons, but also learning about the forces that have shaped the evolution of life on Earth. The study of cosmic rays and their impact on DNA offers an intriguing window into the interconnectedness of life and the universe. These forces, from the solar wind to cosmic rays, remind us of the vast and dynamic environment in which we live and inspire us to continue our quest for knowledge, exploring the unknown with curiosity, innovation, and ambition. Cosmic rays have long been a subject of fascination and intrigue, not only because of their mysterious origins, but also because of their profound impact on life here on Earth. In fact, research has shown that these high-energy particles from outer space don't just influence the evolution of life, but also affect the behavior of organisms. For example, there is compelling evidence suggesting that certain types of cosmic radiation can significantly influence plant growth. In regions with high natural radiation, such as high-altitude areas, plants exposed to increased cosmic rays exhibit remarkable adaptations in their development, resilience, and overall behavior. These adaptations are so unusual that they spark curiosity about how life, in its many forms, can thrive in some of the most extreme and inhospitable conditions known to nature. This intriguing connection between cosmic rays and biological processes extends beyond plants. As we venture further into space, particularly with the ambitious goals of programs aiming to explore Mars and even further, understanding the impact of cosmic radiation on human health becomes more critical than ever. The potential risks posed by cosmic rays, such as an increased likelihood of cancer or cognitive decline, are a pressing concern for astronauts who will face these intense radiation levels on long-duration missions. This realization underscores the urgent need to develop effective measures to safeguard those who dare to explore the far reaches of space. As we continue to study the effects of these celestial phenomena, we uncover a delicate and complex relationship between the cosmos and the life it nurtures here on Earth. But as we turn our gaze outward to the vastness of the universe, one of the most captivating questions that continues to stir our curiosity is the origin of cosmic structures, those awe-inspiring formations such as galaxies, stars, and clusters. Despite decades of astronomical advancements, many of the mysteries surrounding the birth and evolution of these colossal structures remain tantalizingly unsolved. One of the most perplexing questions that astronomers grapple with is how the early universe transitioned from a hot, dense state into the cooler cosmos we observe today, filled with countless stars and galaxies. Decoding this transition is key to unlocking the rich and complex history of the universe itself. At the heart of these cosmic puzzles is the role of dark matter and dark energy, two elusive, invisible forces that make up a significant portion of the universe's mass and energy. Their impact on the formation of structures in the universe is still not fully understood. Current models propose that dark matter served as a sort of gravitational scaffold, pulling visible matter together to form galaxies. However, the specifics of how this process unfolded remain unclear. As scientists delve deeper into simulations and observational data, they aim to better understand the relationships between these enigmatic forces and the visible matter that forms the universe's many structures. These unresolved questions continue to inspire new avenues of research, pushing the boundaries of what we know about the cosmos. The future of this research looks incredibly promising. With the development of powerful new telescopes and satellite missions, such as the James Webb Space Telescope, scientists are poised to gather unprecedented data about the farthest reaches of the universe. These advanced instruments will allow us to peer deeper into space and further back in time, potentially capturing the very moment when the first stars and galaxies formed. Such discoveries could radically alter our understanding of cosmic evolution and may lead to entirely new questions about the underlying physical laws that govern the universe. As we continue to investigate the origins of cosmic structures, these studies may also provide valuable insights into the ultimate fate of the universe. By piecing together how the universe's grand structures formed and evolved, we can better understand the cosmic dynamics that will continue to shape its future. The interplay between structure formation, cosmic expansion, and the influence of dark matter and energy remains one of the most exciting frontiers in cosmology, a field that inspires both wonder and determination in researchers. Every new discovery reveals even more layers of complexity, raising new questions and fueling our quest to understand the cosmos in all its grandeur. Beyond these astronomical pursuits, advancements in quantum physics are also poised to revolutionize space exploration in ways that we are only beginning to comprehend. At the forefront of these advancements is quantum computing, a technology that promises to transform the way we process astronomical data. Imagine being able to analyze data from distant galaxies or exoplanets in real time, far surpassing the capabilities of classical computers. This could enable scientists to make quicker, more informed decisions about which missions to prioritize or which regions of space hold the most potential for discovery. Another exciting frontier in quantum technology is quantum communication. By leveraging the principles of quantum entanglement, researchers are developing nearly unhackable communication systems that could be vital for deep space missions. As spacecraft travel further into the cosmos, maintaining reliable communication with Earth becomes increasingly difficult due to vast distances and interference. Quantum encrypted communication channels could ensure that sensitive data transmitted from spacecraft remains secure, significantly enhancing the safety and efficiency of missions that venture far beyond the reach of our planet. As we stand on the cusp of these groundbreaking discoveries, it's clear that the future of space exploration is intrinsically linked to our understanding of both the cosmos and the fundamental laws of physics. The challenges we face are immense, but the possibilities they open up are equally limitless, inviting us to look to the stars with curiosity, wonder, and the determination to uncover the mysteries of the universe. Moreover, quantum physics is reshaping our understanding of the fundamental forces and particles that govern the universe. As scientists continue to explore the quantum realm, they uncover new and surprising insights that may hold the key to unlocking the mysteries of gravity and space-time. With these discoveries, we could soon develop revolutionary propulsion technologies that could make traveling through space faster, more efficient, and ultimately more achievable. The study of quantum effects in space may offer entirely new ways of movement, opening up the possibility of reaching destinations that were once considered unreachable. By merging quantum mechanics with the exploration of space, we don't just expand our technological capabilities, we also stretch the boundaries of our imagination. Each new breakthrough brings us closer to realizing previously unimaginable feats, such as advanced navigation systems based on quantum sensing, or the ability to comprehend the very fabric of the universe itself. As we gaze into the cosmos, current research provides fascinating clues about the universe's long-term fate. The Big Bang Theory, which posits that the universe began roughly 14 billion years ago in a dramatic expansion, still serves as the foundational explanation of cosmic origins. Since that initial event, the universe has continued to expand, and in recent years, this expansion has been accelerating. The cause of this accelerated expansion is a mysterious force, dark energy, which accounts for a substantial portion of the universe's total energy content. Looking to the future, many scientists predict that this relentless expansion will dictate the universe's ultimate destiny. One scenario, known as the Big Freeze, suggests that as galaxies drift further apart, stars will burn out, exhausting their nuclear fuel. Over billions of years, this will lead to a universe that grows colder and darker, where even the remnants of stars will fade, leaving an almost empty space with only the occasional black hole or neutron star remaining. An alternative theory is the Big Rip. This model envisions a universe where dark energy continues to gain strength, ultimately tearing apart galaxies, stars, planets, and even atomic structures. This catastrophic end would see the universe literally pulled apart on a cosmic scale, with everything from the largest galaxy to the smallest subatomic particle obliterated. While this scenario remains a possibility, it underscores just how little we truly understand about dark energy and its far-reaching consequences. Another theory that has emerged in recent years is the Big Crunch. In this model, gravitational forces eventually slow down the expansion of the universe, reversing its growth and pulling everything back into a singular point, effectively collapsing the universe. Although current evidence seems to suggest this is an unlikely outcome, the idea remains part of ongoing discussions as scientists continue to gather new observational data. Ultimately, although the specifics of the universe's long-term fate remain uncertain, every discovery deepens our understanding of this vast and majestic cosmos and brings us closer to unraveling its countless mysteries. As we venture further into the future, advancements in propulsion technology could dramatically transform human capabilities for space exploration, providing the tools to journey to distant galaxies and unlock new frontiers. Currently, space exploration is limited by the speeds achievable with existing technologies. Even our nearest stellar neighbors are tens of decades away, and the distances between celestial bodies are vast beyond comprehension. However, breakthroughs in propulsion technology could drastically shorten travel times, turning interstellar travel from a distant dream into a tangible reality. One promising avenue is nuclear propulsion, a technology that harnesses the immense energy stored in atomic nuclei. This approach could significantly increase spacecraft speeds, enabling us to travel far faster than conventional chemical rockets. For instance, a spacecraft using nuclear propulsion could reach Alpha Centauri, our closest star system, in just a few months, compared to the 4.5 years it would take with current technology. Such advancements could not only allow us to reach nearby stars, but could also facilitate further exploration of the Milky Way galaxy, bringing distant corners of the cosmos within our reach. Antimatter propulsion offers an even more tantalizing possibility. By tapping into the energy released when matter and antimatter collide, scientists theorize we could develop propulsion systems that reach significant fractions of the speed of light. Such capabilities could allow humanity to journey far beyond our solar system, reaching distant galaxies that are currently beyond our imagination. While antimatter propulsion remains in the early stages of development, the prospect alone has captured the imagination of researchers around the world. In parallel with advancements in propulsion technology, the development of improved life support systems is crucial to the success of long-duration space travel. As we venture farther into the unknown, ensuring the health and safety of astronauts will be of paramount importance. The integration of advanced propulsion with life-sustaining technologies will not only make it possible to explore nearby worlds, but could also pave the way for humanity to embark on intergalactic journeys, potentially redefining our place in the universe. Yet, as we turn our gaze toward distant planets and moons, the ethical implications of space exploration become ever more pressing. One of the most urgent concerns is the potential for contamination. As we send probes to other worlds, there is a real fear that we might inadvertently introduce Earth-based microbes into pristine environments. This could disrupt ecosystems that have evolved in isolation, raising fundamental questions about our responsibility to preserve these extraterrestrial worlds in their natural states, much like how we protect endangered species on our own planet. Another significant ethical challenge is the discovery of extraterrestrial life. Should we find evidence of life beyond Earth, the implications would be profound. How should we approach these life forms? Should we attempt to communicate with them? And what if they are sentient? The philosophical questions here are vast and complex, touching on issues of rights, respect, and the intrinsic value of life forms that may be vastly different from our own. The idea of universal stewardship calls on us to act with responsibility, ensuring that our curiosity does not inadvertently cause harm to other life forms or ecosystems. In addition to these concerns, the potential for colonizing other planets introduces its own set of ethical dilemmas. Should humanity claim celestial bodies as its own, or should we acknowledge that these worlds may hold intrinsic value that we cannot yet comprehend? History has taught us the consequences of colonialism on Earth, and we must be cautious to avoid repeating these mistakes on a cosmic scale. As we venture beyond our planet, we must be mindful of the lessons learned from our own history and strive to create a future of exploration that is not only scientifically groundbreaking, but also ethically sound. The journey into the unknown, driven by the exploration of both quantum physics and space, will continue to challenge our understanding and push the limits of human potential. As we chart the course of the universe, we must balance our thirst for knowledge with an awareness of the responsibilities that come with this newfound power. The future of space exploration is as much about the questions we ask as it is about the answers we seek. As humanity continues to expand its reach into the cosmos, a pivotal question emerges. While space exploration captures our collective imagination, there remains a pressing concern regarding the allocation of resources. The time, money, and energy we invest in missions beyond Earth often lead to a difficult debate. Could these resources be more effectively spent on pressing challenges here at home? Issues such as poverty, education, and climate change demand urgent attention. This dilemma places us at the intersection of our aspirations as space explorers and our responsibilities as caretakers of our planet. Striking a balance between these two ambitions, pursuing the wonders of the universe while addressing the immediate needs of Earth, is an ethical challenge that will influence the course of our future. The way we navigate this challenge may very well shape the trajectory of humanity's journey into the stars. The exploration of the cosmos has often been intertwined with the boundaries of human knowledge. One such boundary was pushed more than a century ago by Albert Einstein's groundbreaking theory of general relativity. This revolutionary framework forever altered our understanding of gravity, suggesting that it is not a simple force acting at a distance as was once thought, but rather a warping of the fabric of space and time itself, triggered by mass. General relativity has withstood the test of time, standing as one of the cornerstones of modern physics. However, as we continue to explore the universe, new observations and theoretical advances hint that our understanding of space-time may be far from complete. Recent developments suggest that our grasp of fundamental concepts, such as time, may still be evolving. Traditionally, time has been understood as a constant flow, ticking away uniformly for all observers. However, general relativity introduced the concept that gravity can alter the passage of time. Near a massive object like a black hole, for instance, time slows down compared to a location far from such gravitational influences. This idea of time dilation, where time is stretched and warped by the presence of mass, fundamentally changes how we perceive the passage of time. But what if emerging theories continue to validate or even expand upon these ideas? Could time itself be more flexible than we once thought, perhaps even behaving differently depending on location? These tantalizing questions open new doors to our understanding of time, suggesting that it may vary in ways we have yet to explore. Moreover, scientists are now probing deeper into the relationship between two of the most significant frameworks in modern physics, general relativity and quantum mechanics. While general relativity elegantly describes the workings of the cosmos on a grand scale, quantum mechanics governs the behavior of particles at the smallest scales. Yet, these two theories, though both profoundly successful in their domains, have not yet been unified. Could there be a deeper connection between gravity and quantum mechanics? Could gravity play a more intricate role in the fundamental fabric of reality than previously thought? These are questions that might soon be addressed through new interpretations of both theories, potentially leading to revolutionary insights into the behavior of time and gravity on both cosmic and quantum scales. Such breakthroughs could rewrite our understanding of the universe and challenge even our most basic assumptions about how the cosmos operates. The journey of discovery is far from over, and as our tools and theories continue to evolve, new revelations await. These emerging perspectives on general relativity and time, along with the ongoing exploration of quantum mechanics, promise to reshape our understanding of the universe in profound ways. Yet, with every new discovery, we are also reminded of how much we still have to learn. In the same spirit of exploration, another frontier in astrophysics that continues to fascinate is the study of sound in space. Though space is a vacuum, devoid of a medium like air or water to transmit traditional sound waves, researchers have uncovered that other forms of waves, such as electromagnetic and plasma waves, can travel through space. These waves carry vital information about the cosmos, revealing hidden phenomena and giving us a new lens through which to examine the universe. By studying these space-based waves, scientists can unlock critical insights into the behavior of stellar bodies, the interstellar medium, and the forces at play within the vast expanse of space. Plasma waves, for example, allow researchers to observe the interactions between solar winds and planetary atmospheres, including Earth's. This information is essential for predicting space weather, which can have a significant impact on our technological infrastructure and even on life here on Earth. In addition to electromagnetic and plasma waves, pressure waves, also referred to as sound waves, are being examined in the context of space, though they behave quite differently from those in an atmosphere. Gravitational waves, ripples in space-time caused by massive cosmic events like colliding black holes, offer another exciting area of study. These waves have been compared to acoustic principles, challenging our understanding of general relativity and prompting scientists to rethink certain aspects of theoretical physics. As we continue to probe the behavior of these waves, new questions inevitably arise, each leading us deeper into the mysteries of the universe and pushing the boundaries of our knowledge. Perhaps one of the most profound and elusive mysteries in astrophysics is the nature of dark matter. This invisible substance, which makes up a significant portion of the universe's mass, remains one of the greatest unsolved puzzles in modern science. Though dark matter cannot be directly observed, its presence is inferred from the gravitational effects it exerts on visible matter, such as galaxies. Theoretical physics plays a pivotal role in helping us understand dark matter, offering models that describe its potential properties and behaviors. These models are often grounded in advanced mathematics and can lead to predictions that scientists test through observation. One of the most exciting possibilities surrounding dark matter is that it may consist of particles that interact weakly with normal matter, making them incredibly difficult to detect using traditional methods. High-energy particles provide an exciting avenue for exploring dark matter, offering a glimpse into its elusive nature. As scientists continue to push the frontiers of knowledge, we may be on the brink of discovering new ways to observe and understand dark matter, bringing us one step closer to unraveling one of the most profound mysteries in the cosmos. In the grand scheme of things, each of these pursuits, whether it's the search for new understandings of time, the exploration of cosmic waves, or the hunt for the nature of dark matter, serves to deepen our connection to the universe. Every discovery expands the horizon of human knowledge, offering new insights into the forces that shape our reality. And as we continue to explore, the promise of new revelations beckons, reminding us of how much is yet to be understood about the universe in which we reside. When high-energy cosmic rays collide with dark matter particles, they can trigger detectable outcomes, producing faint radiation signals. This phenomenon offers scientists a unique opportunity to explore the elusive nature of dark matter. By using advanced particle accelerators and cutting-edge observatories, researchers can search for these faint signals, gradually piecing together the possible characteristics of dark matter. But the study doesn't stop there. The detection of high-energy neutrinos has provided additional clues, giving scientists another way to trace the presence of dark matter. Neutrinos, which are ghostly subatomic particles that interact minimally with matter, are thought to stream from regions of high dark matter density, such as the centers of galaxies. By closely observing the distribution and behavior of these particles, physicists hope to gather valuable insights into the nature of dark matter, its mass, how it interacts, and how it behaves within larger cosmic structures. This research highlights a synergistic approach to understanding dark matter. On one hand, theoretical models offer hypotheses about how dark matter might exist and behave, while on the other, high-energy particle physics provides tangible evidence to test these ideas. Together, they illuminate the complex fabric of our universe, shedding light on the mysteries of a substance that makes up about 25% of the cosmos. As technology and experimental techniques continue to advance, scientists' understanding of dark matter is poised to evolve. This progress not only deepens our comprehension of this enigmatic component of the universe, but also enhances our overall understanding of the dynamic interaction between visible and invisible forces in the cosmos. Recent developments in the modeling of neutrinos have opened new doors in astrophysical research, unlocking the potential to solve some of the universe's most profound secrets. Neutrinos, due to their incredibly weak interaction with matter, have long been a challenge to detect. Despite their elusive nature, these particles are crucial carriers of information from some of the most energetic and far-reaching processes in the universe, such as supernovae and the merging of neutron stars. By refining our models of neutrinos, scientists have begun to understand their behavior, how they are produced, and how they interact. This deeper understanding of neutrinos also sheds light on the fundamental processes that shape the universe, particularly in the creation of elements. During the explosive deaths of massive stars, large quantities of neutrinos are released, playing a crucial role in the synthesis of the heavy elements that form planets, stars, and indeed life itself. As scientists continue to study neutrinos, they gain a deeper appreciation of the universe's evolution, from the smallest subatomic particles to the grandest galaxies. Moreover, neutrinos serve as a unique tool for investigating cosmic events that are invisible to traditional electromagnetic observations, such as visible light. When neutrinos are detected from distant astronomical phenomena, they provide an entirely new perspective, acting as messengers that offer clues about events occurring far beyond our current observational reach. This approach enables scientists to piece together the history of the universe in a novel way. As our models of neutrinos become more sophisticated, they not only deepen our understanding of the cosmos, but also challenge and refine existing theories. These ongoing efforts could lead to groundbreaking discoveries about the universe's structure, its behavior, and its ultimate fate. In fact, the study of neutrinos has the potential to illuminate some of the darkest and most remote corners of the cosmos, transforming our understanding of everything from asteroid belts to black holes. The insights gained from this research could reshape our perceptions of reality itself. Another fascinating avenue of exploration in theoretical physics is cosmic string theory. This theory proposes that the early universe may have contained one-dimensional defects known as cosmic strings, which are akin to an immense, stretched-out thread. These strings are thought to have formed in the moments immediately following the Big Bang due to phase transitions in the fabric of spacetime. This process, known as symmetry breaking, leads to the creation of these cosmic strings, which could stretch across vast distances of space. The study of cosmic strings offers a fresh perspective on the universe's evolution. Given their immense density and gravitational influence, cosmic strings could have warped spacetime in such a way as to affect the formation of galaxies and other cosmic structures. Their gravitational effects might have acted as seeds for matter, encouraging the formation of clumps that eventually grew into galaxies. In this way, cosmic strings could be woven into the very fabric of cosmological development. Interestingly, cosmic strings may also hold the key to understanding dark matter and dark energy. Some scientists hypothesize that these strings could interact with known forms of matter, providing a window through which to observe these mysterious components that account for much of the universe's energy content. By investigating the interactions between cosmic strings and dark matter, researchers hope to unlock pathways to a more comprehensive understanding of the cosmos, both on a large scale, examining the structure and formation of galaxies, and on a small scale, delving into the fundamental components of matter. Exploring cosmic strings does more than fuel our curiosity about the universe's origins. It also deepens our understanding of its ongoing evolution. This research is at the intersection of cosmology, quantum physics, and general relativity, promising to unravel the forces that shape the cosmos and continue to influence it today. As we explore these intriguing cosmic anomalies, we move closer to a fuller understanding of the universe's vast, intricate nature. As we gaze upward beyond our planet's atmosphere, the vast cosmos unfolds with secrets waiting to be unlocked. Cosmic strings, hypothetical one-dimensional objects that could stretch across the universe, serve as a fascinating thread weaving together the mysteries of the universe, from its inception to its eternal expansion. These enigmatic structures might hold the key to understanding the origins and future of space itself. However, it is not only the trained experts and elite institutions that are contributing to this monumental task. In fact, amateur astronomers, often considered the hobbyists of the cosmos, play an unexpectedly pivotal role in the field of astrophysics, providing valuable, crowdsourced data that can lead to groundbreaking discoveries. With the advent of increasingly sophisticated technology, individuals equipped with telescopes, cameras, and the power of the internet can now make their observations accessible to researchers across the globe. This collective effort has significantly augmented the pool of astronomical data, far surpassing the capabilities of any single institution. It is this vast, worldwide network of skywatchers that has become integral to advancing our understanding of the universe. One of the most remarkable contributions by amateur astronomers lies in their observation of variable stars, celestial objects whose brightness fluctuates over time. By monitoring these stars and meticulously recording their brightness variations, amateurs provide data that helps scientists better understand these stellar phenomena. This, in turn, allows researchers to establish patterns, calculate distances, and gain deeper insights into the life cycles of stars. These contributions are crucial in piecing together the cosmic jigsaw puzzle that is the birth, evolution, and death of stars. Moreover, amateur astronomers are often the first to detect explosive cosmic events, such as supernovae, cataclysmic explosions marking the death of a star. When an amateur astronomer spots such an event, they can report it swiftly, alerting professional astronomers to mobilize resources and study the phenomenon in real time. These timely reports are critical for capturing the fleeting moments of these violent yet awe-inspiring cosmic occurrences. Furthermore, the unique perspectives and diverse locations of amateur astronomers enable them to witness and record transient events, brief yet significant occurrences in the sky that might otherwise go unnoticed. For example, dedicated skywatchers have discovered new comets and asteroids, while others have captured rare and beautiful celestial phenomena such as meteor showers or eclipses. The influence of amateur astronomers extends beyond mere observation. Their data often sparks further research, leading to unexpected discoveries about the dynamics of the universe. Through their contributions, they help to shape and expand our understanding of space in ways that might have been unimaginable just a few decades ago. In turn, the collaboration between amateur and professional astronomers fosters a vibrant community of science enthusiasts, all united by their desire to unravel the mysteries of the cosmos. By sharing their findings through online platforms or collaborating directly with research institutions, these amateurs play an indispensable role in pushing the frontiers of knowledge in astrophysics. As the realms of astronomy and machine learning converge, we stand on the precipice of a new era in space exploration. With the tremendous amounts of data generated by advanced telescopes, satellites, and space missions, traditional methods of analysis are often overwhelmed by the sheer scale and complexity of the information. This is where machine learning, an area of artificial intelligence designed to analyze and recognize patterns in data, becomes a game changer. Algorithms trained on massive data sets are capable of extracting valuable insights, identifying subtle patterns, and even predicting the behavior of celestial phenomena, all at speeds and accuracies that humans alone could not achieve. This combination of machine learning and astronomy holds the promise of faster discoveries and a richer understanding of the universe. One of the most compelling applications of machine learning lies in the identification of celestial objects. Stars in their infancy, distant galaxies, and even exoplanets, planets orbiting stars beyond our solar system, can be difficult to detect due to the presence of noise within the data. Machine learning algorithms excel at filtering through this noise, revealing hidden features and allowing astronomers to locate rare and elusive objects. In essence, machine learning has the potential to enhance the efficiency of astronomical observations, increasing the likelihood of discovering new and important cosmic objects that might otherwise have been overlooked. Machine learning can also aid in understanding the dynamics of cosmic events like supernova or black hole collisions. By analyzing existing data, algorithms can predict the behavior of these events, providing deeper insights into the underlying physics of such extreme phenomena. These predictive models not only deepen our understanding of the universe's most violent occurrences, but may also help astronomers anticipate future events, enabling them to prepare for real-time observations. This capability could prove to be invaluable for studying the most powerful and dramatic events in the cosmos. Furthermore, the integration of machine learning into the realm of astronomy opens up new avenues for public engagement. As these algorithms become more sophisticated, the insights they generate could spark greater public interest in space exploration. Citizen scientists, amateur enthusiasts who contribute to scientific research, could even participate in this process by helping train and refine machine learning models. This democratization of knowledge and technology fosters a greater sense of connection between humanity and the cosmos, making the mysteries of space more accessible and intriguing to the general public. Looking ahead, the collaboration between machine learning and astronomy offers unprecedented potential for unlocking secrets that have eluded scientists for centuries. With new algorithms and tools at our disposal, we stand at the threshold of discovering phenomena previously beyond our reach. It is through advancements like these that the wonders of the universe are slowly being brought into clearer focus, pushing the boundaries of what we know and transforming our understanding of the vast, ever-expanding cosmos. Nanotechnology, the manipulation of matter on an atomic and molecular scale, is another area that is making profound contributions to space exploration. One of the most exciting aspects of this technology is its ability to create materials that are not only lighter, but stronger than anything we have previously used. These advanced materials hold the key to creating spacecraft that are more efficient and capable of reaching farther into the depths of space. The reduction in weight allows these spacecraft to carry more scientific instruments or payloads, which could help gather more detailed data or explore more distant regions of the cosmos. Imagine a space probe capable of traveling deeper into the vast unknown of the universe, or a satellite with enhanced precision and data collection capabilities, all thanks to innovations in nanomaterials. These breakthroughs promise to make space exploration more efficient, cost-effective, and transformative. The possibilities seem endless as technology continues to evolve, offering us new tools to explore and understand the universe at levels previously thought to be out of reach. Nanotechnology is reshaping the future of space exploration, offering capabilities that were once considered out of reach. This revolutionary field allows the creation of ultra-sensitive instruments capable of detecting even the faintest signals from the furthest reaches of the cosmos. Through nanoscale sensors, scientists are now able to measure even the smallest fluctuations in temperature, magnetic fields, and chemical compositions. These minute detections have transformed the way we explore celestial bodies. Whether studying the characteristics of distant planets, the composition of asteroids, or the behavior of faraway stars, these advanced sensors provide a level of detail previously unimaginable. As a result, researchers can now gather data that deepens our understanding of the universe in ways that were once impossible. One particularly compelling application of nanotechnology in space exploration is its role in energy generation and storage. Nanostructured materials have the potential to revolutionize solar panel technology, making them far more efficient at capturing energy, even in the harsh environment of space. This leap in efficiency directly translates into longer, more sustainable missions, allowing spacecraft to remain operational for extended periods, far beyond current limitations. Similarly, advances in nanotechnology are leading to the development of batteries that are lighter, last longer, and charge faster. This has profound implications for spacecraft that require long-term autonomy, as they can now operate for prolonged periods without the need for frequent resupply. The integration of these tiny materials is setting the stage for a new era of space exploration, one where the boundaries of possibility are continually pushed. As we venture further into the unknown, nanotechnology offers a glimpse into what might be achievable in the near future, inspiring generations of scientists, engineers, and explorers to reach for the stars. The breakthroughs driven by these nanoscopic wonders are poised to reshape not only our view of space, but also our very understanding of what is possible in the realm of space exploration. Simultaneously, the rise of quantum computing is ushering in a new era of processing power, transforming how we analyze vast amounts of astronomical data. Traditionally, analyzing the immense quantities of data collected from the cosmos has been a daunting challenge, often requiring supercomputers that can take significant amounts of time to process. With the advent of quantum computing, however, we're entering a phase where the principles of quantum mechanics allow computers to process data in ways that traditional machines simply cannot. The strength of quantum computers lies in their ability to simultaneously handle an enormous number of variables, enabling astronomers to explore multiple possibilities and outcomes at once. This is particularly important when studying complex cosmic phenomena, such as the formation of galaxies or the behavior of black holes, where intricate calculations could previously take weeks or even months. Quantum computing promises to reduce this processing time drastically, allowing researchers to draw conclusions more quickly and make new discoveries faster. Moreover, the synergy between quantum algorithms and machine learning is set to revolutionize the way we classify and analyze astronomical data. Machine learning, which helps scientists sift through massive data sets, is now poised to benefit from quantum computing's efficiency. Algorithms powered by quantum technology can process data far more effectively, leading to faster and more accurate classifications of celestial objects, as well as the detection of rare and elusive astronomical events. This has profound implications for the search for exoplanets and tracking the movement of asteroids, enabling scientists to better understand the origins and trajectories of these distant bodies. But the potential of quantum computing extends far beyond mere speed and efficiency. It is poised to open entirely new avenues for breakthroughs in theoretical physics. For example, quantum computing could play a crucial role in unraveling the mysteries of dark matter and dark energy, enigmatic components of the universe that remain elusive despite decades of study. As this powerful technology continues to evolve, it may provide the key to understanding the very fabric of the cosmos, offering answers to questions that have baffled scientists for centuries. The combination of quantum computing and space data processing is an exciting frontier in the study of the universe. It holds the potential to unlock the secrets of the cosmos at a pace never before imagined, bringing us closer to answers about the fundamental forces that shape our reality. Over the years, the trajectory of space exploration instruments has mirrored our ever-growing ambition and understanding of the universe. From the early days of telescopes with simple glass lenses to the cutting-edge technologies of today, these instruments have served as both tools of discovery and symbols of human progress. Galileo's telescope, for instance, was instrumental in revealing the complexity of the cosmos, challenging long-held beliefs about the structure of the universe. This technological leap set the stage for a deeper understanding of celestial bodies, sparking a revolution in our view of the universe. The evolution of these instruments continued in the mid-20th century with the advent of radio telescopes. Unlike optical telescopes, radio telescopes could detect and study phenomena invisible to the naked eye, such as the rhythmic pulses of pulsars or the cosmic microwave background radiation that provides clues about the universe's earliest moments. This period of scientific advancement is often seen as a pivotal moment in astronomy, where researchers began to push the boundaries of existing theories and explore new, uncharted realms of knowledge. The space age brought even more dramatic advancements. The launch of satellites and space probes like the Voyager missions expanded our tools of exploration, providing unprecedented data from other planets and moons. These missions gave us the first clear images of distant worlds, along with invaluable insights into their atmospheres and surface compositions. As nations and space agencies collaborated on these ambitious projects, the world witnessed the power of international cooperation in scientific research, fostering a shared vision of uncovering the mysteries of the universe. Today, we stand on the precipice of a new era with the James Webb Space Telescope, one of the most advanced observatories ever constructed. This instrument is designed to peer into the earliest stages of the universe, uncover the nature of exoplanets, and investigate the elusive components of dark matter. Historians of science recognize the James Webb Space Telescope not just as the next step in our exploration of the universe, but as a milestone that encapsulates humanity's unrelenting desire to understand our place in the cosmos. As we reflect on the evolution of space exploration instruments, it becomes clear that they are much more than sophisticated tools. They represent humanity's unending curiosity and determination to push the limits of what we know. Each instrument is a testament to our quest for knowledge, a symbol of our collective desire to explore and understand the universe. The discovery that Earth's conditions might not be as unique as we once believed has profound implications for how we view our place in the cosmos. In the past, Earth was often seen as a solitary oasis in an otherwise barren and lifeless universe, a planet with the right climate, water sources, and conditions to sustain life. However, recent findings suggest that such conditions may not be as rare as previously thought. The search for other Earth-like planets has shown that the universe might be teeming with worlds capable of supporting life, potentially transforming our understanding of the cosmos and humanity's place within it. This realization opens up new avenues for exploration as we consider the possibility of life beyond our planet and begin to reassess what makes Earth and life so special. The increasing evidence of Earth-like exoplanets and the discovery of diverse environments that could potentially support life elsewhere in the cosmos is fundamentally reshaping our understanding of the universe. This growing body of evidence urges us to reconsider humanity's place within the vast, uncharted expanse of space. One significant consequence of this realization is the evolving approach that scientists are taking in their quest to detect extraterrestrial life. Missions to Mars, the icy moons of Jupiter and Saturn, and even the study of the atmospheres of distant exoplanets are no longer solely about exploring and understanding the worlds we already know. They are increasingly focused on finding signs of life beyond Earth. If Earth is not as unique as once thought, then the building blocks of life could be scattered across the universe, embedded in a multitude of environments. As a result, the search for chemical signatures of life has become a central theme of astrobiology. This shift in focus has brought a new sense of urgency and excitement to the field, fostering the development of innovative technologies and methodologies that may one day uncover hidden life forms across the cosmos. The very notion that Earth's conditions might be replicable on other planets challenges our preconceptions about the singularity of our home. It opens the door to a deeper understanding of how geological and atmospheric processes critical to sustaining life can occur under a wide variety of circumstances. With this knowledge, scientists can create a more nuanced and comprehensive framework for studying planetary systems, guiding future efforts to assess the habitability of planets orbiting distant stars or moons within our own solar system. Such understanding also aids in predicting how life might adapt to the differing conditions found on other worlds. This evolving perspective pushes us to question not only where life might exist, but also what forms it could take. Our philosophical understanding of life itself begins to shift as we entertain the possibility that Earth is not the only cradle of life in the universe. The question then arises, how likely are we to encounter intelligent beings? What will our interactions with extraterrestrial life, if discovered, reveal about humanity's place in the larger cosmic narrative? As we dive deeper into these questions, the implications of discovering that life may exist elsewhere become more profound. This realization drives us not only to explore further, but also to marvel at the vastness of the universe and the shared cosmic story that binds all life, terrestrial or otherwise. The discovery of exoplanets, planets that orbit stars beyond our solar system, has fundamentally altered the way we think about Earth's uniqueness, as astronomers discover planets of all shapes, sizes, and atmospheric compositions. They not only highlight the singularity of our planet, but also challenge previous assumptions about what makes a planet capable of supporting life. Reports of rocky planets, gas giants, and even worlds rich in water have broadened our understanding of planetary formation and evolution. For example, the discovery of planets in the habitable zone of their parent stars, where conditions could allow for the existence of liquid water, bolsters the idea that life could emerge on planets with a wide array of characteristics. This highlights that not all planets are barren and lifeless, as was once assumed. In fact, some exoplanets have atmospheres rich in elements that were once thought to be incompatible with life as we know it. This has prompted researchers to explore alternative biochemical pathways that life might take, challenging our Earth-centric view of biology. On the other hand, the stark contrasts observed between different exoplanets emphasize the rare and special conditions Earth enjoys. With its perfect distance from the sun, protective atmosphere, and abundance of water, Earth stands out as an extraordinary oasis in a sea of inhospitable worlds. Some gas giants, found in close orbits to their stars, experience extreme temperatures and radiation, serving as reminders of how precarious the balance of conditions necessary for life can be. These contrasts not only inspire awe, but also reinforce our appreciation for Earth's complex climate and the myriad factors that sustain its ability to support diverse ecosystems. The ongoing study of exoplanets invites us to reconsider our place in the cosmos. Each new discovery challenges our understanding of the potential for life beyond Earth, while deepening our comprehension of what makes our planet so remarkable. As we continue to explore distant worlds, we are constantly reminded of the fragile nature of our own planet and the cosmic story to which it belongs. This exploration ignites an insatiable curiosity, encouraging us to not only protect Earth's delicate environment, but also to continue our quest to unlock the mysteries of the universe. Earth holds a unique place within the Milky Way galaxy, nestled in one of its spiral arms known as the Orion Arm. This region is home to a rich array of stars, nebulae, and other cosmic phenomena. The understanding of Earth's location in the galaxy has evolved significantly over time, from the belief that Earth was the center of the universe to the realization that it is just one of countless celestial bodies. For much of history, many cultures held to the geocentric view, believing that Earth was the center of everything, with the sun, moon, and stars revolving around it. However, during the Renaissance, figures like Copernicus and Galileo challenged this view, revealing that Earth is merely one planet orbiting the sun, which itself is just one star among billions within the galaxy. As astronomy advanced and space exploration began, our understanding of the universe grew even more profound. We learned that the Milky Way is a barred spiral galaxy stretching roughly 100,000 light-years across, containing approximately 200 billion stars. Earth, orbiting the Sun at a distance of about 93 million miles, resides in a relatively quiet region of the galaxy, a neighborhood that offers both advantages and disadvantages for life. Today, we no longer see Earth as the center of the cosmos, but rather as a unique cradle of life in a vast, ever-expanding universe. Scientists continue to investigate how our solar system fits into the broader structure and history of the galaxy. This perspective reminds us of the fragility and wonder of our existence and prompts us to consider, are there other Earth-like planets out there, teeming with life scattered throughout the depths of the Milky Way? The journey to understand Earth's role in the universe invites both curiosity and awe. As we contemplate our small yet significant place in the cosmos, we are reminded of the delicate balance that sustains life on our planet. Climatic changes on Earth have played a pivotal role in shaping not only the evolution of our own species, but also our understanding of how life might exist elsewhere. Throughout history, Earth has experienced remarkable climate fluctuations, from ice ages to periods of intense warming. These changes have influenced ecosystems and the course of evolution, providing valuable insights into how life adapts and survives under varying conditions. By studying these fluctuations, scientists refine their models for potential extraterrestrial life, helping to broaden the scope of where and how life might arise beyond our planet. One of the most intriguing areas of study in this context is the existence of extremophiles, organisms that thrive in the most hostile environments on Earth. These include bacteria that live in boiling hot springs, deep ocean vents, and even those that flourish in freezing temperatures. By studying how these resilient organisms adapt to extreme conditions, scientists can expand the potential habitats for life elsewhere. For example, if life can survive in the boiling waters of an earthly hot spring, could similar life forms endure in the high-pressure oceans of Europa, one of Jupiter's moons, or in the harsh, dry environment of Mars? Furthermore, Earth's fluctuating climate forces scientists to consider the role of environmental stability in the development of complex life. For much of Earth's history, the planet has oscillated between stable and extreme climatic conditions. By constructing theories that balance these fluctuations with the likelihood of supporting life, researchers are gaining a better understanding of how both stable and unstable climates might nurture life. This opens the door to exciting hypotheses about exoplanets, not just those with stable climates, but those that might harbor life in less than ideal conditions, challenging the very definition of habitability and expanding the boundaries of where life might be found in the universe.